you achieve not only academic excellence by way of a teaching learning process led by domain experts and scientists as faculty, industry-driven curricula, research and innovation avenues, and technology-enabled learning, but also holistic development with emphasis on employability and placements and numerous student-centric initiatives. One such initiative is the Study Abroad Program, or SAP, wherein you can pursue part of the semester at Amity campuses in New York, Singapore, London, Australia, and Dubai, and prepare to be a global corporate citizen with an exposure to foreign culture, industry, and economic dynamics. Amity also offers you a basket of career-focused disciplines in all streams of interest to Class 12 students like you. Let's take a glance. The pulsating campus life at Amity University, Gwalior, is an enriching experience which allows you to flourish as an individual. By organizing and participating in diverse cultural events and competitions such as Youth Fest or being a part of Sangathan, the Inter-Amity Institution's sports meet that marks the birthday of Amity's founder president, you get countless opportunities to enhance your organizational teamwork and leadership skills.
At Amity University, Gwalior, you follow a learning and development curve that is designed to help you stay ahead of the future by empowering you to dream and carve out a vision. It has been conceived to help you optimize your true potential. So if you see yourself joining the League of Indian Visionaries shown earlier, then go ahead and envision a better tomorrow for yourself and for India.
A very warm and pleasant morning, ladies and gentlemen. I, Dr. Rinku Bhatia, accord a warm and cordial welcome to you all to the inaugural session of 1-week national workshop on advanced synthesis and characterization techniques organized by Department of Applied Physics, Amity School of Engineering and Technology, Amity University, Madhya Pradesh. It is a proud privilege and honor to have with us distinguished guest, Professor Dr. Pramendra Vajpayee, Vice Chancellor, Jayaprakash University, Chhapra, Bihar, Professor Dr. A.K. Singh from IIT BHU, Honorable Pro-Chancellor, Lieutenant General V.K. Sharma, Ati Vishesh Seva Medal, Dr. Anil Vashish, Officiating Vice Chancellor, HOIs, all the members of faculty, participants, attendees, staff and students. I once again welcome all the respected guests and thank you all for sparing your valuable time to be with us today. In the recent decade, technology in material science and engineering has advanced dramatically in numerous disciplines. Progress in these areas will be paced more by the timely availability of well-characterized advanced materials. There are numerous challenges in the preparation and characterization of sophisticated new materials. Novel advanced techniques are constantly emerging, joining characterization techniques that have been practiced for centuries. The National Workshop, being held from 8th to 14th August 2024, offers a dynamic platform for researchers, faculty, and industrial participants to boost morale by enriching their learning and understanding about advanced synthesis techniques, characterization tools, interpretation, and analysis of obtained data. Let us move to the proceedings of the workshop by offering a mantra of Ma Saraswati, Goddess of Knowledge. Ya Devi Sarvabhuteshu Vidya Rupen Sansita Namastute 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 Namo Namah. Amity University, Madhya Pradesh has been awarded as the best private university of Madhya Pradesh twice under the influential and charismatic leadership of our Honorable Pro-Chancellor Lieutenant General V.K. Sharma. Under his able guidance, right from 2011 till today, university has grown by leaps and bounds towards excellence and has been ranked amongst top 200 universities in the country in the NIF rankings and has been accredited by NAC. Also, Amity School of Engineering Technology has been ranked #1 private university institute in Madhya Pradesh. Now, may I request our Honorable Pro-Chancellor Sir for his opening remarks. Please, sir.
Very good morning, Dr. Rinku Bhatia, Professor Dr. Pankaj Mishra, Dr. Manisha Singh, the Director of ESSET, Dr. Anil Vishish, the officiating Vice Chancellor, and on behalf of all faculty members of ESSET and all students, I extend a very hearty welcome to Professor Dr. P.K. Bajpai, the Honorable Vice Chancellor from Jayaprakash University, Chhapra, and also to Professor Dr. A.K. Singh from IIT, Banaras Hindu University, and also to all those who have joined online for this one-week workshop commencing today and which is likely to finish on 14th of August 24. The topic for the workshop, which is advanced synthesis and characterization techniques, is very apt because today the world requires technologies to meet the requirements of power, to meet the requirements of living space as the world population goes on increasing, to meet the needs for industry, production all around, and also for research outside the planet which is going on. So for all these, new materials are required, and so are the techniques to discover and synthesize these materials, and also the techniques to characterize them, and also to find out the new parameters by which the characterization could be done, and those which could be beneficial to us for research purposes and for well-being and improving the quality of life of human beings on this planet. When the scientists study about advanced materials, my view on the subject is that we need to consider first the impact on the environment. Any new material which is discovered will always have some impact, anything which is synthesized, because when it comes to synthesis, it means you are trying to create something which is not originally existing in nature, right? That is why you are trying to get something. Although you are getting it from nature itself, but you are trying to create something which is not existing in its form that you synthesize in nature. So such a thing will always have some impact on the environment. The impacts may be in short-term basis, or if not found out now, maybe in long-term basis, which we do not know. A simple example is the plastics. When they were invented about 70, 75 years back, at that time, everyone was gaga, saying that look at the amount of their utility, look at how cheap they are as compared to other materials, how convenient they are. But today we have realized their impact and we are trying to ban plastics, especially single-use plastics, because they are polluting the environment, a thing which was not probably realized at that time. Today, everybody is talking about nanomaterials, their usefulness to the research, their usefulness in strength of materials, and so many other things, including the batteries, power packs, etc. But the impact of nanomaterials on human health, human well-being, and on pollution that they might cause to the environment is not yet fully known. Which will be known maybe in the long term, if at all it exists. Maybe we wish that it does not exist. So therefore, any new material which is being synthesized and being put to use for scientific work or for making the life of human beings more comfortable or for meeting our needs with regard to our well-being, for our health, for our medicines, etc., needs to be analyzed also from the point of view of environment, long-time and short-time analysis. Next, I would like to mention is about the cost benefit analysis. In our enthusiasm to go in for new materials to synthesize them, usually at times we tend to forget about cost, because we as scientists and in the world that we live in, we feel that better to go in with our research without finding out what will be its cost and when it will be actually put to use if the cost is very prohibitive. And also the quantities that can be produced, whether those quantities are apt or not. Two important things which I feel today deserve attention. One is about the batteries. All devices which are operated by internet or connected to the net or used for communication or used for even space journey, they require power. And the power has to come either from the batteries or it has to be self-generated using the power of the sun or the natural parameters which are there, like the water or like the sea waves or the air velocity, etc. So all these, the materials which are required for batteries is one area of research which is rapidly being researched upon and the materials are being synthesized. Here again, the disposal of the batteries and the cause of pollution that they can cause possibly to the sand or the earth, to the air, to the water is also to be taken into account. The materials like lead, cobalt, which are highly, or mercury for that matter, which are commonly used, or sodium, which are commonly used in batteries, or potassium. So these all materials are highly toxic in nature and their disposal has to be done in a specific manner, otherwise they will pollute, and from that pollution, the soil, we get the food which goes into the cycle, food cycle into our bodies and causes damages. Another area which is of important, I feel today, is construction. The methodology of brick construction and materials which were erstwhile used like cement, traditional materials, needs to undergo a change. It is undergoing a change. There are portable houses which are being now considered, which can be dismantled with ease and can be put to use, which are very cost effective, which are cheap, light, robust, regenerative, reduced rubble, reduced impact of environment, reduced pollution, reduced impact on land, water and space is what is required today as far as construction materials are concerned. Construction activity is something which are not going to stop because the population growth is not going to stop so soon. It is envisaged that the population will continue to grow on this planet up to 2050. Thereafter, it might start declining unless some catastrophe strikes. With that kind of a situation which is prevalent, new constructions will be required and will keep taking place. Expansion of cities will keep happening because more population is migrating towards cities gradually. And the weight of the materials itself is causing problems, especially when the construction is happening at places like hill areas. You've seen the impact of the type of constructions which have happened in Uttarakhand, in India. We have also seen the impact also of the global warming and changes which are taking place because of excessive pollution in the air, primarily because of construction materials which is happening. And of course, pollution which is happening because of the exhaust from the vehicles. These two are the major factors for pollution in the air and in the land that we are seeing today. As far as characterization techniques are concerned, there are many techniques which are there and they have undergone quite a bit of change. New parameters and new ratios are being looked upon, and a lot of work is going on in all these directions. So therefore, the topic for the discussion that we'll have now for the next 1 week on advanced synthesis and characterization techniques is something which is going to impact all of us in one way or the other without our even knowing about it. So I'm sure the researchers, some of them who are listening to me, and also some of the think tanks who are sitting here today will give a heed to what I've said. And I think there's a lot of room for introspection and for taking our research in the right direction so that the impact on environment, the cost benefit analysis versus the usefulness of the product that we are going to synthesize should be taken into account. I convey my congratulations to Director ASET, Dr. Vikas Thada, Dr. Vivek Jaglan, Dr. Pankaj Mishra, Dr. Manisha Singh, and their team who have organized this workshop, which will give insights into various aspects of advanced synthesis and characterization techniques. I wish the workshop a great success and hope that it will be an excellent learning opportunity for the young students and the scientists who joined online, and they'll benefit from all this. So thank you very much. Jai Hind, best wishes.
Thank you, sir, for setting the right tone of the workshop. Your words of wisdom have always inspired us and guided us. We have with us distinguished guest, Honorable Vice Chancellor of Jayaprakash University, Chapra, Bihar, Professor Dr. Pramendra Vajpayee. Dr. Vajpayee is a material scientist with the doctorate from Physics Department, Northeastern Hill University in 1988. He worked for Northeastern Hill University from 1988 till 1996 and then joined Guru Ghasidas University in 1996. Since 1996, he became the head of Pure and Applied Physics, Guru Ghasidas Vishwavidyalaya, Bilaspur, India, and served as Dean Sciences and Physical Sciences. He has held number of academic responsibilities like Director IQAC, Coordinator Technology Enabling Center sponsored by DST, Convener NEP 2020 Task Force, etc. He has also held number of additional charges like Head Sophisticated Analytical Instrumental Facility, Coordinator for National Knowledge Commission Network-based activities, Chairman Core Committee Integrated Management System, etc. He has published more than 217 papers in reputed journals and have more than 100 papers in conference and symposium proceedings, and edited 2 books published by AIP USA and Anamya Publications, New Delhi. He has received more than 10 awards for his contributions to the science. He is a fellow of International Academy of Physical Sciences, full member of American Nano Society, and executive editor of Chhattisgarh Journal of Science and Technology. He is also the regional editor of International Journal Research published from Maxwell Publications. He is reviewer of many reputed international journals. Professor Vajpayee has delivered more than 50 lectures in various international national conferences, including more than a dozen keynote addresses, and chaired technical sessions in seminars. He has supervised 10 PhD and 24 MPhil dissertations. He has organized 24 conferences and 1 international conference, and has provided academic leadership by establishing Department of Pure and Applied Physics, Institute of Technology at Guru Ghasidas University, and developed a 3 megavolt particle accelerator based interdisciplinary research center with the financial support from DAE and UGC of approximately 40 crores. His research has led him to visit various countries like Japan, Italy, Thailand, South Korea, USA, etc. He holds positions in number of statutory bodies of the number of universities and has more than 10 funded projects to his credit. May I now request Dr. Vajpayee to kindly enlighten us with his words of wisdom. Please, sir.
Honorable Pro Chancellor of Amity University, Madhya Pradesh, Lieutenant General B.K. Sharma ji, Honorable Vice Chancellor of the University, core committee members, Dr. Pankaj Misra ji, Dr. Manisha Singh ji, and other members. It's a great pleasure for me to participate in this very innovative workshop on advanced material synthesis and characterization. For last 36 years, we have been involved in developing new materials, developing new characterization techniques, and creating a multidisciplinary environment so as to provide the multifunctional materials for various disciplines. And therefore, I think I am one of the learners who will be most benefited by such kind of workshops. Recently, Department of Science and Technology, Government of India have started Stuti workshops. And last year we organized, when I was in Guru Ghasidas Vishwavidyalaya, one such Stuti workshops. And from the feedback of such workshop, what we find, and even from discussion with many eminent scientists working in various fields, the way 21st century science is developing, as rightly said by Lieutenant General B.K. Sharma ji, that role of material development and vis-a-vis environmental degradation and climate change has to be looked into very carefully. Another important aspect that he has touched upon is the kind of new technologies that are coming up. Say, for example, nanotechnology, biotechnology, bioremediation, and the role of multidisciplinary characterization techniques in developing the sustainable solutions for industrialization, especially Industry 4.0 onwards. We require a new outlook, a new focus on how we have been using the material development and various kinds of synthesis and characterization techniques. The discipline based, as a material scientist of myself, we have seen the evolution of synthesis strategies and characterization techniques, especially in India, and we have come a long way in both. Earlier, our objectives has to be the fundamental understanding of materials. And I have been involved in basically three fields: developing the complex metal oxides for various usages, including the ferroelectric materials, ferromagnetic materials, multiferroics, developing the nanomaterials, especially the semiconductor nanomaterials for various technologies, and controlling the basic parameters like the size, shape, morphology, and functionalities of these materials. And third, when we develop the accelerator facility or the ion beam facility at Bilaspur, in terms of the 3 MB pelletron based accelerator, there also we try to give an alternate of top down and bottom up approaches in nanotechnology. A third approach, ion beam assisted nanoparticles formulation approach. In India, we have now a number of UGC DAE facilities. I think that is a very important point that we have to focus in such workshops to the newcomers, new researchers who have the vision, who have the energy, who are focused, to definitely tell them that characterization techniques have evolved in India enormously. Now we have the Indus 1 and Indus 2 in Indore as a national facility where almost the whole electromagnetic spectrum is there ready to provide the most advanced characterization of materials. This facility is free to be used, Students are provided projects, and Center for Advanced Technology Indore is also existing there. This should be used. In addition to this, we all know that we have the inter-university centers. Inter-university center in Indore, inter-university center at Calcutta, at Mumbai, and the inter-university accelerator center at Delhi. Similarly, we have the many facilities of DAE at Kalpakkam, DRDO facility at Hyderabad, and most recently the STEM facility at Indian Institute of Science, Bangalore. It is providing you the ready-made database of what kind of characterization facilities are available in India. And anybody can use with a very nominal charge. These are in addition to the sophisticated analytical instrumentation facilities that we have all over the country. Apart from this, in this last 10 years, there has been a drastic change, especially after the introduction of National Education Policy 2020. The way we have been doing research and the way the material preparation and characterization have changed. Now, the researchers and researches are not for production of papers, patents. It is more of providing the challenging solutions, sustainable solutions for the local, regional, and national importance problems. I'll discuss, I don't know how much time I have been given, but I will give just one or two examples. I know this is the inaugural session. People don't have much time, but just say, for example, drug delivery system is one of the major challenge in the biomedical research. Many of the critical diseases requires the drugs to be delivered at the spot. And many kinds of strategies have been adopted. However, in India, still we are facing a major challenge of having a sustainable, smart drug delivery system. This is a challenge that can be met out by the active coordination of people who can design and develop nanoparticles, people from biotechnology, biochemistry who can design the receptor molecules, people who can understand the toxicological problems of the so-called physiology of the body, and the people who can really understand the bioefficacy of developing these drugs and delivering them to the site. In carcinogenic research, the chemotherapy effects, we all know how many negative effects are there, and therefore there is a urgent need of forming the teams, the cluster research in these areas, developing the new nanomaterials, apart from the metal nanomaterials that have been developed for this, developing the new receptor molecules that are more constant-free, that are stable in the physio pH, developing the new toxicological routes, and developing the new bioefficacy understanding of these things. This is a real challenge in India to meet out the effective strategy of minimal drug delivery for especially carcinogenic diseases. Another area that requires the urgent need of new bio-nanotechnological advances is the transforming the waste into best. And especially the environmental waste in our rivers, in ponds, it is creating havoc. And there are no effective strategies in terms of the large-scale solutions to meet out how to convert the bioremediation routes using the new advanced materials. This is the second important thing. Third thing, as we all know, जो हरियाणा, पंजाब और दिल्ली के आसपास के क्षेत्रों में हर साल जब पराली जलाई जाती है, that kind of problem is also a challenge. There are many such challenges one of the challenge or of the success story that has been successfully met out by one of our colleague, Professor Thomas in Kerala. That is transforming the rubber industry by using the mixing of nanoparticle effectively and increasing the mechanical strength of rubber, increasing the corrosive strength of rubber, and many such things. There are many stories we can go on, but what I mean to say that the role of material scientists in designing the new material routes for synthesis and the equally good characterization techniques is the need of the hour, not only from academic point of view, but to provide the challenging solution for the industrialization. And therefore, this workshop I find is a very good efforts to provide a platform to our young researchers, learn new techniques. Certainly, you must be having the karke seekho or the hands-on some training on various fundamental characterization in material science, like how to use the X-ray diffraction in an advanced rocking curve. People don't know the efficacy of rocking curves, like in the SAM, AFM, STM, or the morphological techniques that we are using very routinely. In addition to this, I think there is a time when advanced spectroscopic techniques must be reviewed and introduced. The third type or fourth type of technique that must be pushed into are the accelerator-based characterization techniques or the ion beam assisted techniques that are not very popular in India. I suppose in the field of environment science, the role of Pixie is very much there. The role of Rutherford backscattering is very much there. And especially the role of multidisciplinary characterization is very important and must be highlighted in this workshop. I'm sure that this workshop will be very useful academically, in terms of networking and in terms of forming the teams so as to provide the sustainable solutions using the various techniques of material science. We have some of the challenges in high advanced areas of technologies for material scientists. As we all know, one of the field you have already introduced is the battery research. We need better SOFC materials. We also need India as a powerhouse of new fuels, especially the hydrogen fuel research. And its transformation as an industry has taken up in India in last 2-3 years. As a director of Technology Enabling Center, I had the opportunity of working with some of the industries in Punjab who are converting the waste into the hydrogen fuel. And there are very interesting problems that need to be solved using the chemical engineering, using the nanotechnology, using the mechanical fields, and such interdisciplinary and multidisciplinary researches will provide the boost to the already emerging economy of India. I'm sure that this workshop will be very beneficial to the participants, and I wish the workshop all the best, very success. Thank you very much for providing me this opportunity to say a few words. Thank you very much.
Thank you, sir, for enlightening us about research facilities, areas, and new materials development. I also thank you for throwing light on new research areas, research avenues in materials for various applications. I hope the participants will sever the knowledge in their future endeavors. Thank you so much. Now, I would like to also welcome Dr. Jai Singh from Guru Ghasidas University, who has been instrumental in organizing this workshop by event. So this is all from the inaugural session. Now let us move towards the proceedings of this national workshop. So the first speaker for this workshop is Dr. Akhilesh Kumar Singh. I welcome you, sir. Dr. Akhilesh Kumar Singh is professor in the School of Material Science and Technology since January 2024 at IIT BHU, Varanasi. He has served as assistant professor from 2005 to 2014 and associate professor from 2014 till 2023 in the School of Material Science and Technology, IIT BHU. He has worked as coordinator of the School of Material Science and Technology during the period 2017 to 2020 and again working as a coordinator since 2023. He has more than 24 years of research experience. He has supervised 20 PhD theses and 57 MTech theses. He has published more than 100 papers in peer-reviewed journals and conferences and has been published 3 patents. His research interests include structure property correlations in materials, X-ray and neutron powder diffraction analysis, synthesis and characterization of advanced materials, photovoltaic solar cell materials, phosphor materials, polymer composites, etc. His projects include DST FISC Level 2 project of approximate 395 lakhs, SERB project on development of high TC lead-free piezoelectric materials for energy harvesting of approximately 52.70 lakhs, DRDO project on development of ferroelectric and earth magnite-based radar absorbing materials for stealth applications of approximately 25 lakhs, the ITMI bill project, Indo-Russian project on novel multifunctional magnetic, ferroelectric and semiconductor effects in solid solutions of ternary magnetic perovskites, etc. He has the membership of number of professional bodies. He is Joint Secretary of Indian Crystallographic Association. He has been Executive Council member in Indian Crystallographic Association from 2016 to 2019. He is a member advisory committee on physical sciences, Council of Science and Technology, Uttar Pradesh. He is a life member of Indian Crystallographic Association and life member of Materials Research Society of India. He has received multiple awards like awarded BHU Gold Medal for Outstanding First in MTech Materials Technology, received Best Poster Paper Award at 15th Annual General Meeting of Material Research Society of India held at IIT BHU. Then again Best Poster Paper Award in the 17th Annual General Meeting of Material Research Society of India at Lucknow University 2006, etc. He has organized number of conferences and workshops on material science. His research quest has led him to visit number of countries like Russia, Japan, Italy, etc. And he has more than 2,600 citations to his credit. We are honored to have with us Sir A.K. Singh, sir. And now I invite him for his talk on basics of fluorescence, spectroscopy and applications. Please, sir.
Thank you, madam, for kind introduction. So, I am audible, I think.
Yes, sir.
Thank you. So, Honorable Pro Vice Chancellor, Sharma sir, Bajpayee sir, other distinguished guests, faculty members, students, friends. So, very good morning to all of you. So, this is a very well designed workshop that meets the requirement of recent researchers, covering all the characterization and synthesis method to say. So I will just share my screen. Is it visible?
Yes, sir. Yes, sir.
Thank you. So whenever we study any material, suppose we develop any material, so you always see that very first step is to know about the material that you have synthesized is had formed or not. That is the very first step. The next thing is, will it show the desired properties? That is the very first step for a material scientist or materials researcher. The next thing is materials being used under application. then you may need to assess its performance or life, how it is working well, or has it degraded later on during application. So all these things become quite easier when we use X-rays. So either you are a scientist or researcher or a common man, most of the people are familiar with X-rays. So because it's used in medical diagnosis also. So whenever somebody is having some fracture or some kind of other medical illness, so people say that to go for X-ray, and doctor, based on the examination, gives some advice or treatment. So that's why X-rays, most of the common people are familiar. When we come to scientists and researchers, we mostly do X-ray diffraction. So in medical diagnosis, we do X-ray imaging. In research, we do X-ray diffraction. So X-ray diffraction is the most powerful tool, and that is involved as the very first basic step to check about whatever material you have prepared had been formed, or there are some impurities or any other issue. So we will try to learn how we can characterize a material. So as informed to me, it's a diverse audience, UG, PG, PhD and faculty members. So I had to plan my lecture in such a way that everybody can gain something. Everybody could get some knowledge about it. It cannot be very advanced that UG students or PG students don't understand the thing. And at the same time, it should be useful enough for advanced researchers and faculty members. So I have tried to compile the lecture considering some fundamentals of X-ray crystallography, and then some case studies, some examples of materials characterization. So I hope that it will be beneficial for you. So whenever you develop any material, you have to characterize this. So X-ray diffraction method is mostly used for solids. So you talk about any solid. So it can be either crystalline or amorphous. That is the common feeling. There are two classifications we have. In crystalline systems, what we get, there is a regular periodic arrangement of atoms or molecules, a systematic regular periodic arrangement. In amorphous solids, the atoms or molecules, they are irregularly arranged. At the same time, there are some materials which are partly crystalline and partly amorphous. So some fraction is crystalline, some fraction is amorphous. That we often see in polymers as well as glass ceramics. There are some metal alloys which are quasi-crystalline, slightly not very common to all the researchers. Now, if we come to the crystalline systems, they can be either single crystalline or polycrystalline. So two classes. So in polycrystalline set, you have lots of crystals joined together, whereas in single crystal, the entire piece is just one crystal. So if you look for a material which is crystalline, the example shown here is gold and sodium chloride. So what we see, you can see the gold atoms, they are systematically arranged in a quite straight line or say regular periodic fashion. So you know size of an atom, how small it is. Say sodium atom or chloride atom, how they are arranged alternatively together. So it's a very fascinating thing. So one may wonder how they are organized together. So just consider the case, if I give you some say 10 cricket balls and tell you just arrange them in a straight line. So if you try that, so unless you use a ruler or some assistance for drawing a line and then putting it there, it will definitely become irregular. It will not be perfectly linear straight arrangement. So how so small atoms they get organized so systematically in a regular periodic fashion? So that comes from the energy consideration. So if you consider a material, when it forms, when we bring two atoms close to each other, so you know, the interatomic potential varies like this curve. So energy is minimum for some equilibrium separation. And if we increase that separation, energy of the solid will increase. If we decrease that distance, again the energy will increase. So when we have a dense ordered packing, the system is having most of the distances that corresponds to equilibrium distance between two atoms. So it has somewhat lower energy in comparison to when you have irregular packing, random packing. So this energy minimization criteria compels a material, a solid, to organize itself in a regular periodic fashion. Then one may wonder why there are amorphous solids. Every solid should be crystalline. Why not so? The reason is very simple. Whenever you develop a material, when you are synthesize a material, so it happens that you have not given it enough time to organize in a regular systematic way. So during synthesis, if you provide a long time duration, favorable conditions, it will definitely organize itself in a crystalline fashion. So as you see in glasses, most of the silicate glasses, they are amorphous because when you cool down from the liquid melt, so viscosity increases very high. So atomic molecular mobility ceases out. So they don't organize themselves in a regular fashion. Whatever liquid phase arrangement was there, that gets frozen. Okay. The same thing happens in many of the polymers. So you have very long polymeric chains. So arranging them in a regular periodic fashion, that also becomes difficult. Okay. So it's just a schematic figure for a crystalline amorphous thing, a polycrystalline and single crystal. So if material is polycrystalline, you have many small pieces which join together to give the complete entire piece of the material. Whereas in single crystal, from one end to other end, you will have regular periodic arrangement of the atom. The regularity and periodicity will not be broken anywhere throughout the solid. So most of you are well familiar with the all known crystalline materials. We can classify them into one of these 7 crystal systems: cubic, tetragonal, orthorhombic, hexagonal, monoclinic, triclinic, and rhomboidal or trigonal. Okay. So there are very good textbooks. Many of you might be already well aware of these things, so I will not go into. So coming back to X-rays. So you know it's electromagnetic radiation discovered in late 1905 by German physicist. So you know, whenever we have some scientific discovery, so sometimes it takes quite long time to come into application. You have discovered something, but coming into application for human life, that takes a longer gap. But X-rays, they quickly came to application with X-ray imaging in medical diagnosis, and then later on by the scientist in X-ray diffraction. So electromagnetic radiation, there is a wavelength range which we classify as X-rays, but for a diffraction experiment, there is a requirement that interplanar separation of the crystal should be comparable with the wavelength of the X-ray which are being used. So that's why the spectrum is limited for only those wavelengths which are close to the interplanar separation of the crystal. So there are several techniques apart from X-ray diffraction or materials characterization. So I will not go into, maybe you will be taught by some other speakers. The next thing is how they are produced, X-rays. So it's very simple. We take some high atomic number metal, bombard it by accelerated electrons. These electrons knock out some inner shell electrons by transferring their kinetic energy. So when a vacancy is created, a higher orbital electron jumps to the inner orbital, and then the difference of the energy that is emitted in the form of X-ray wavelength. Okay. So this is basically another schematic picture of a X-ray tube where we have a electron gun from which electrons are incident to the target metal, and then the X-rays are emitted and they are taken out by some small window opening. Normally it's a beryllium window. Okay. Now, because you know there are many orbitals or energy levels in the atoms, so corresponding to electronic transition, corresponding to different energy levels, there will be many X-ray wavelengths. But when we are going to characterize our powder X-ray diffraction, you need just one wavelength, monochromatic wavelength. So for that purpose, the K alpha wavelength is the most strongest. So we select that wavelength. Okay. So one needs to separate out the K alpha wavelength, for which we use monochromators and filters. So this is the spectrum of molybdenum. You can see there are strong K alpha 1 and K alpha 2, two lines, two components are there, and a K beta line. So K beta is filtered by using some appropriate filter that depends upon what type of target metal is. So that one can suitably choose. So after filtering, you can see in this right figure, K beta is minimized. So you have still two wavelengths, K alpha 1 and K alpha 2. So most of the X-ray laboratory X-ray machines, they have these two wavelengths. So whenever you record the X-ray diffraction pattern, so you may see just one line, but especially at the lower angles, but they consist the overlapping two lines corresponding to K alpha 1 and K alpha 2. At high to theta angle, you will see that they are separate. Okay. So I will show in later slides. So this is again radiography that is used for medical diagnosis, also in security systems. XRD, EDX, these are the characterization techniques. We are restricting to XRD only. So the fundamental basic principle for X-ray diffraction characterization comes from the Bragg's law, which says that lambda is equal to 2d sine theta, where d is the interplanar spacing corresponding to a particular set of atomic planes. So you know, when you will be having a regular periodic arrangement of atoms, you can define several atomic planes. And different types of atomic planes, they will have different interplanar spacing. So depending upon that, a particular angle theta satisfies the Bragg condition corresponding to which you get the diffraction lines. Okay. So this is another schematic diagram. So as you define a unit cell in a crystal, say regular periodic arrangement of atoms making a unit cell, so one can see a bottom plane, intermediate plane, and top plane. So when X-rays interact with these planes, basically the electron cloud of atoms, they get scattered in all possible directions. But when Bragg condition is satisfied, as per the Bragg's law, you get the constructive interference, and then the intensity is maximized for the diffracted rays that you can record in diffraction pattern. Okay. So if we record a diffraction pattern, you take any sample, any solid sample, record its diffraction pattern in laboratory XRD machine. So you know, X-ray diffraction machines, they are normally of two types: single crystal diffraction machine and powder X-ray diffraction machines. So most of the X-ray instruments which are available in common research labs, they are powder X-ray diffraction machines. Some researchers who work on single crystals, they take the single crystal machine. Okay, but the diffraction pattern will be a different thing. In powder X-ray diffraction pattern, when you record the data, you will get an image like this. So x-axis is the diffraction angle, which is measured at 2 theta. So that's easy to measure. So because the incident X-ray beam and diffracted beam, those directions you know, so you can easily measure the angle between them. So that's why x-axis is always shown as 2 theta, not the theta. So that you get in diffraction pattern. Y-axis shows the intensity of the diffracted X-ray lines. Okay. So suppose you don't know any fundamental of crystallography. You are not a crystallographer. You don't have much knowledge about crystallography. But you want to gain some information by X-ray diffraction. So just record the pattern. If you are having a crystalline system, you will get pattern like this, the top image. Well-defined peaks at some given 2 theta angles. Whereas in case of a amorphous solid, which is not crystalline, or if you have a liquid, you will get a very broad peak. So you don't have any knowledge of crystallography. But looking at the pattern, anybody can easily distinguish, oh, this material is amorphous, this material is crystalline, because they are giving a particular type of diffraction image, diffraction pattern. Okay. Now, there can be situation in between. A material which is partly amorphous and partly crystalline. So what kind of diffraction pattern you will get? This right figure you can see. A broad hump kind of thing that corresponds to the amorphous fraction, and then overlapping sharp diffraction lines that corresponds to the crystalline phase. So you can easily say that the material is partly amorphous and partly crystalline. That is not the complete job done. You may also like to know what fraction of the solid is amorphous, what fraction of the solid is crystalline. So that you can also determine. We will discuss in coming slides. Okay. As I mentioned, a single crystal can have a completely different kind of diffraction pattern. You get well-defined diffraction spots. I will not go into because it will need a completely another lecture for discussing the analysis method and other things. Okay. In fact, electron diffraction spots in TEM, they also come like this, and the analysis principle are somewhat similar. Okay. Now, you have suppose a powder X-ray diffraction pattern. So what sort of informations you can see here? So for a crystalline solid, you have certain positions, 2 theta angles, where you are getting some diffraction peaks. Next thing is the intensity. Okay. One peak is weak, another is strong, another further weak, then strong. So this you call as intensity distribution of different diffraction peaks. That is another information that you can collect from this pattern. The next information is the peak shape. So you can see there is certain peak shape and then there is certain peak broadening. So peak shape and peak broadening. That is another information contained in the diffraction pattern. Okay. So position of diffraction peaks, peak intensity, shape, intensity distribution as a function of diffraction angle. Okay. So only these informations you get from a diffraction pattern for a powder sample. But only using these three informations, you need to extract all the information about the crystal, lattice parameter, crystal type, crystal system, its space group, position of atoms in the unit cell, bond lengths, bond angles. So all these information one can extract just by using these three informations. So one thing I would like to mention, before you record a diffraction pattern, specimen preparation is also important. So for a powder method, it will be a very fine, it should be a very fine powder, and then it should be mounted at the exact position as per the focusing geometry of the instrument. Otherwise, you will get erroneous data, and then any analysis will also have incorrect information. Okay, because that will affect the intensity and shape of the peaks in the diffraction pattern and sometimes position also. Okay. So as I mentioned, these are the informations that you can extract: amorphous or crystalline. How many crystalline phases are there? That you can also determine. What are their relative proportions? That you can also determine. Crystallite size, sometimes particle size as well. What is the size of the individual crystal? That's mostly important in nanomaterials. Strength, a material can have some inbuilt strength. Lattice parameter, atomic positions, bond length, and many other information. Okay. So normally when you go for a X-ray diffraction data collection, so normally one can use powder. That is preferred one. That is the preferred form of the sample for powder X-ray diffraction analysis. But that's not always case. You may not have a powder sample always. If you are working on metals, so making a metallic powder is not so easy. Sometimes you don't want to destroy your sample by converting it into powder. You want to have some other characterization on metallic plate. Sometimes you have some polymer film or any other thin film deposited on a substrate. There also you can't make its powder. So what are the limitations? If you are having a powder sample, you will have an ideal X-ray diffraction pattern as expected from the fundamentals of crystallography, the scientific principles of crystallography. But if you have a plate or thin film, so that may introduce some artifacts in the recorded diffraction pattern. One thing that may appear, the intensity of the diffraction lines, they may get altered because of the form of the sample. A plate may have preferred orientation of crystal. A thin film can also have preferred orientation of certain atomic planes. So that will modify the intensity of diffraction lines. Another problem that arises when you have a plate, say metallic plate or thin film or ceramic pellet, you try to mount it. So it will be having some finite thickness. So in powder sample, you press it inside a sample plate groove so that its surface appears exactly at the position as desired from the focusing geometry of the instrument. But if you have a metallic plate or film, so it may get placed slightly forward or backward at the sample stage in the machine. So that will introduce another error. Peak shape may get modified. Peak positions can also shift. So that is termed as the sample displacement error. So that may get introduced in the diffraction pattern. Some peaks may get shifted higher angle sides. Some peaks may get shifted slightly lower angle side. So your analysis may get affected. So if you are an experienced researcher, you can easily identify if that kind of problem is there or not. If not, you can definitely use the diffraction data for further analysis, especially for determination of lattice parameter or other things. Okay. In powdered X-ray diffraction machine, you have two types of data collection: continuous scan and step scan. So in continuous scan, the X-ray detector is given some fixed rate at which it will move in the at different diffraction angles. In step scan, you define some 2 theta interval that's called as step, 2 theta step, and then you define certain time that for this much time detector will stay there and record the diffraction count. So this step scan strategy is adapted if you have to see very weak reflections in the diffraction pattern which are not being seen in the continuous scan. Otherwise, normally continuous scan is recommended for usual analysis of the materials. Scan speed is another important thing. So suppose you give the measurement command for say 2 theta 20 to 100 degrees centigrade. Now you define the speed at which speed the detector will move. So if you give fast speed, it will measure the pattern quickly, say 10 minutes, 15 minutes, 20 minutes. Okay. But what will be the consequence? Overall intensity of the diffraction pattern will be somewhat lower. If you give slow scan, so it will move slowly in the same 2 theta range. So it will take more measurement time, but the diffraction peak that you will get, they will be stronger. Okay. Another thing is in laboratory X-rays, you define tube voltage and tube current. So if tube voltage, tube current is high, you will get more intensities because the X-ray beam has more photons. So in that scenario, you can have faster scanners. Okay. So now I will take some of the case studies for X-ray diffraction analysis. The very basic first step is phase identification. So suppose you prepare a material. You want to confirm it has formed or not. So this image shows the X-ray diffraction pattern for copper and its oxide, CuO. Okay. So what we see here, copper and copper oxide, the number of diffraction peaks, they are different, quite different, or same 2 theta angle. Peak positions, they are also different. Intensity distribution is also different. Okay. So like our fingerprint, the thumb impression, the X-ray diffraction patterns, they are the fingerprint of materials. Every material has its own diffraction pattern. No two common materials will have same diffraction pattern. What is the reason? The size of the atoms in the solid will be different. If you take a different material, the crystal structure will be different. interplanar separating lattice parameters, they will be different. So when you record the pattern, you will get different position of peaks, and depending upon the crystal structure, different number of diffraction peaks. So just by recording the diffraction data, by looking at the diffraction peaks, you can clearly identify that this pattern is from this particular material. Okay. So now, to help with the researchers, when people prepared or characterized different kind of materials, so one international body started making a database of diffraction pattern. So earlier it was famously known as JCPDS files. That stands for Joint Commission on Powder Diffraction Source. So that international body started maintaining the database of the diffraction pattern of different materials. Later on, there is ICDD data, International Center for Diffraction Data, that maintains the database. Some other bodies are now also there which maintain the diffraction database. So this database comes in CD, you can purchase, you can take online subscription also. So where you get the database of the diffraction pattern of different materials. So when you are characterizing your material, just compare its diffraction pattern from the patterns in the database. When it matches with a particular type of material, you can easily tell that this kind of material is there in the sample. Another example. So copper, the top pattern is there. You get some peaks. It has been treated to make some Ayurvedic medicine by IMSBHU. So there is oxidation of copper that makes copper oxide for one first treatment. Second treatment, the remainder copper is disappeared. So earlier there was copper oxide and copper both, but that has got disappeared. Then copper oxide. Another treatment, again some additional peaks, they are getting modified. Okay. Another example, for copper sulfide, some medical treatment, say this, they heat and provide some Ayurvedic herb during heating. So they get different kind of compounds that's used as medicine. So one can use the International Diffraction Database to identify what type of material is there in your sample. But that is not the complete story. You may prepare a new sample. You may develop a new material. You may synthesize a new material whose database is not available. Then what to do? So this is another example which is shown here. So bottom pattern is from zinc ferrite, ZnFe2O4. It is available in the database, ICDD database. The file number is 89-7412. So students synthesized zinc copper ferrite. Okay. So zinc is just 0.2, copper is 0.8, and then Fe2O4. So you will not get in the database because this is a new material. Then what to do? So first stage is, whenever you develop a new material, you know what are the ingredients. You have some idea that what kind of crystal structure may appear. So you try to match it with the diffraction pattern of similar compounds. So a similar compound is zinc ferrite. So if you compare the diffraction pattern, so you can see number of peaks are same and positions are also close. So one can clearly say that the two compounds, they are isostructural. They have the same structure. The only difference is that the composition is different. So the interplanar separations will be different in atomic planes, and the lattice parameter of the crystal will be different. So that one can determine by analyzing. How, that we will discuss. Just wait. Another thing is, whenever you develop a material, so you use certain parameters. So some temperature at which you are heating the material. In solution farming, you control the pH of the material, dilution of the solution, some temperature or any other parameter, okay, during synthesis. So changing the synthesis conditions, they can modify the product material, or sometimes they may lead to impurities. So one needs to know that what is the optimum synthesis condition. So what is the solution? You record the diffraction pattern of the material for different synthesis conditions, and then do the phase identification. Okay. And then you can clearly tell the material has formed or there are certain impurities. So in this example, bottom pattern is from lead oxide. The next pattern is another reactant, magnesium, niobium, titanium oxide. Two materials, they were mixed together and heated at different temperatures, that is written. Okay. Just to form a product. It's a piezoelectric material, PMNPT, lead magnesium niobate, lead treatment. Okay. So one can see when we heat at 600 degrees centigrade, the powder mixture, there are multiple peaks. Okay. Some of them correspond to the reactants as well. There are some new peaks also that corresponds to product, but the unreacted material peaks are also there. So what to do? Increase the synthesis temperature, 650. You can see still some additional peaks are there. Further increase the temperature. The intensity is going down, slight peak. Further increase the temperature, 750. Further increase the temperature. So in the top pattern, you can see only product peaks are there. The diffraction peak for the product phase. Rest of the peaks has got disappeared. So same kind of optimization you can do with your synthesizing material, changing pH, or taking different kind of reactant material, or using different kind of reactant solution, any other parameter which decides the processing. Another important information that people are usually interested in, the crystallinity and phase fraction. So if you are having a partly amorphous, partly crystalline system, that usually happens with polymers or glass ceramic, or you are having the crystalline system, but it has multiple phases, multiple crystalline phases, one type of phase, other type of phase. So how to determine their fractions? That is another important information. So this is another case study, a representative example. So that fraction peak that you see here, that is from PC PMMA blend. So PC is polycarbonate and PMMA polymethyl methacrylate. So two polymer, they are mixed together to make a blend. Okay. Just for some application, in different proportion, in different ratio. So in this top corner, you see 10% PMMA is added, then 30% pure polycarbonate, 20% PMMA. So different compositions of the blends. Now how the crystallinity is getting modified, that we need to know by changing the composition. So the analysis is very simple, anybody can do. You don't need much knowledge of crystallography. Just you have to separate out the broad background peak which corresponds to amorphous content, and then the narrow peaks which correspond to crystalline phase. Okay. So using any standard plotting software, you can simply fit the peak profiles. So like Origin, Excel, or any other plotting software, you just try to fit peaks. So normally these peak profiles, they are Gaussian, sometimes Lagrangian can also be little bit. Say pseudo-wide peak profile shape is used. So by that you can fit the narrow peak region. So these two peaks are fitted here, you can see for the peaks, and then a amorphous blue background peak is fitted. So two crystalline peaks, one amorphous peak, that is in blue color. Okay. Now determine area under curve. So software can easily tell you about the area under these peaks. Now using this area, the simple formula for crystallinity, you can determine the fraction of crystalline phase. Area under peaks for crystalline component, so these two peaks, divided by area under amorphous component as well as area under crystalline component. So that gives you the fractional crystallinity. You multiply by 100, that will give the proportion of the crystalline phase, crystalline sample. Okay. So as you can see in this inset, as we modify the composition for different weight percent of PMMA, the crystallinity is continuously changing. It is basically decreased. Okay. So anybody can use this method to determine the percentage crystallinity. Okay. Another case can be there where you have both the materials as crystalline, but there are two phases, a product phase and a impurity phase. So that you can determine by comparing with the International Crystallographic Diffraction Database, that what are the peaks which correspond to the product, what are the peaks which correspond to impurity or unreacted material. Okay. Now you need to know the percentage. What fraction of impurity is present? So one can do same kind of exercise as we did earlier. But in crystalline systems, one can have multiple peaks. So it may be very much time consuming. Or sometimes peaks are very weak, you cannot easily determine. Okay. So we use a shortcut, some approximation. Take the intensity, just intensity of the strongest peak for the product phase and intensity of the strongest peak for impurity phase. Okay. So these are impurity peaks. Okay. So just measure the intensity. Now using these intensities, you can have some estimation of percentage impurity and percentage of product. So intensity of the impurity phase peak, strongest peak in fact, divided by the intensity of the impurity peak and intensity of the product. Okay. So that tells about, for this X-ray diffraction pattern, there is roughly 1.5% the impurity phase. Okay. Keep in mind that this is just approximation. If you need to know the precise fraction, you need to bring in the structure factor information also, because type of the atoms which are present in the unit cell are impurity peak, impurity phase, they will be different from the product phase. So intensities can vary because the structure factor will change. So one has to take into account those factors also. So there is an advanced technique, Rietveld structure refinement, Rietveld structure analysis, that can precisely tell about the relative proportion of different crystalline phases. So there is another speaker who will talk about the Rietveld structure analysis, so I will not go into. Another important information that researchers are often interested, especially with the nanomaterials, the crystallite size. So whatever sample they have prepared, what are the size of the crystallites? Crystallite size. So that information can be extracted by the peak width of the diffraction lines. So this full width at half maxima, that is the term which is used, FWHM. So that is measured by simply you measure the intensity of the peak, do its half, come to that intensity position, and then measure the width. So this information is used to determine the crystallite size. So the peak width that has multiple contributions. So the width of the diffraction peak that have different contributions. So size is definitely one important factor. Apart from that, some broadening comes from the instrument side. So if you use different instrument, say one diffraction machine, another diffraction machine in a different lab, for same sample, you may get different peak width. Sample is same, but full width at half maximum will vary, because instrumental width can be different. Okay. So ideally, as per Bragg's law, 2d sin theta is equal to lambda. One expects a sharp line, a sharp diffraction line, a point line. Okay, like this. But you get some finite width that comes from the instrument side because of the divergence of the X-ray beam. You cannot make it strongly collinear, and other parameters are there. Okay. So some finite broadening will always be there, irrespective of your sample is having the size broadening or not. This broadening is very small if you use synchrotron source. So synchrotron XRD sources are special. In those cases, you get very huge intensity of X-rays. So you can afford to narrow down the beams and make a very small broadening of the peaks. Okay. Other thing can be strain. So sample may have some residual strain. So that also contributes to the line broadening. Some sample defects. So when you make the atomic substitution, when you prepare solid solution, when some vacancies are there. So in those cases, some defect broadening can also be there. So one need to separate out different components just to get the crystallite size component to determine the size. So one can see here, considering all the contributions, you get the total FWHM for the red peak. Okay. So one need to separate out the other contributions. So what we do, we record the X-ray diffraction pattern for some ideal sample in the X-ray machine. So these standard samples, they normally come with the laboratory machine. When you purchase a machine, normally silicon powder, sometimes CO2 powder, any powder which is having a bigger crystallites. So size dependent broadening is not there, which is not having any defect. Okay, which is defect free, which is strain free. So when all other contributing factors are not present, so when you record the diffraction pattern, whatever broadening comes in the line, that is corresponding to instrument. So now you know what is the instrumental broadening. Okay. So you subtract that broadening from the full width at half maxima of your sample, which you are analyzing. Okay. And then using the Scherer formula, one can determine the crystallite size. Okay. So this is another example. A nanocrystalline sample is heat treated at different temperatures. Okay. 700, 800, 900, 1000 and 1100 degrees centigrade for certain hours. Okay. Only one peak is shown here, just for clarity. So what you see? The peak width with increasing the heat treatment temperature is decreasing. Okay. That happens because the crystallite size increases when you increase the temperature. So nanomaterial try to increase its size by particle size growth or grain growth to minimize the surface area. Okay. So that the surface to volume ratio is minimized. System tries to become more stable. Okay. So now you measure the full width at half maxima, subtract the instrumental broadening, the full width at half maxima that you have got for the silicon sample, standard sample, and then you use it in this formula. So D is the crystallite size, average crystallite size. Lambda is the wavelength of the X-ray which is used to record the diffraction pattern. Theta is the diffraction angle. And beta is the full width at half maxima of the X-ray diffraction line. Okay. So ideally, one can use any peak to apply this formula. Okay. But we use the strongest peak because in that the full width at half maxima determination will be more precise. Okay. At the same time, one should also take care if there are multiple peaks in the diffraction peaks. So better to choose another peak which is having just single peak. Okay. That is another thing. Now, when you measure this FWHM, this is in 2 theta units. So using it into the Scherer formula, you need to convert it. So you cannot directly use in 2 theta units. So it is converted into radians. So after converting into radians, you put the value that is beta in this formula and you will get the crystallite size. So in this case, you can see for different heat treatment temperature of the sample, the size is increased. Okay. Now there is another issue. When you increase the size, full width at half maxima is decreasing. So this is a table. You can see the bottom row for 5 nanometer sample. The full width at half maxima is 0.0291. And in degrees, it is 1.745. Okay. For higher crystallite size, it is decreasing. Okay. For 100 nanometer, you get 0.099 in degrees, and in radians quite small. Now this 0.099, it comes quite closer to the broadening, instrumental broadening that you have recorded for standard. So when they come close to the instrumental broadening, this method is not applicable. Okay. So results may not be that much precise, and especially for bulk sample, there will be no size broadening. Okay. So for bulk crystalline sample, size broadening is not there because basically the Scherer formula is based on the limited number of parallel atomic planes that contribute to the broadening of the diffraction line. So if number of planes become quite large, that comes to the microcrystalline sample, a bulk sample, you will not get the size broadening. So it's not applicable for microcrystalline or bulk sample. Sometimes people do erroneously, who are not well aware of the fundamentals, they do erroneous analysis. So this is another example, a powder material, it's a piezoelectric sample. A powder material is ball mill, high energy ball mill for different time durations. Okay. So in bottom sample, you see multiple peaks. As you increase the ball milling time, broad peaks, only broad peaks survive. Okay. Broad. So that becomes because of the decrease in the size of the crystals. So for a bulk sample, you can see a CM image, the grain size. You have bigger crystallites. Okay. After ball milling, they become nanocrystalline, about 50 nanometer. Whereas in bulk sample, it was 1 to 3 micrometer. Okay. Now there is another issue that often researchers do the mistake. Crystallite size and particle size, as well as grain size as well. What are the differences? Sometimes people exchange them without knowing what are the cases, which type of term has to be used. Okay. So crystallite size is especially determined from Scherer formula. Okay. And that we determine for nanocrystals, not for the microcrystals, bulk crystals. Okay. Now, a particle can have multiple crystallites. Okay. So if particle is having many crystals, some boundaries are resolved in this TM image. Say particle size will be large than the crystallite size. You may have a case where all the particles are monocrystalline. There is only one crystal. All the particles are monocrystalline, isolated. So in that scenario, the crystallite size and particle size, they will be comparable because crystal is one individual unit and all the particles, they are also monocrystalline. So sizes will be compared. Otherwise, particle size will always be bigger. Okay. In grain size, that we usually define for bulk compact piece, where we record a cross-sectional image of the same. Normally in optical microscopy or SEM, okay, say cross-section of the surface. Okay. So the interface between two crystals that defines the grain boundary and this size, the breadth of one grain, that is in fact a crystal, a one unit crystal that defines the grain size. Okay. Now, the other fact, strain. Say material apart from size broadening, it can have strain as well. So how to determine that? So now broadening is added up with the strain contribution as. So the total broadening after subtracting the instrumental broadening will consist of a crystallite size component and a strain component. Luckily, the theta dependence of these two contributions are different. Okay. One varies like this for crystallite size, another varies like this, a tan theta dependence for strain. Okay. So Williamson plot Hall analysis, that's based on the name of the scientist. So they devised this method to determine the strain as well as grain size. Okay. So you take multiple peaks, determine their full width at half maxima. I can show here. So multiple diffraction peaks, determine their full width at half maxima, and using that, you plot it as Sine theta and beta cos theta. Okay. So sine theta, you know, the peak position. This b cos theta, that is full width at half maxima of the diffraction peaks. That you can easily plot. So for different peaks, you will have many data. Now you try to fit it with a straight line. So slope of this straight line, as per this expression, the bottom expression, slope of this line will determine the strain contribution, and the intercept at the y-axis, that will determine the size contribution. So if there is no strain in the sample, you will get a parallel line to the sine theta axis. If there is no size broadening, the line will pass through origin. There is no intercept. Okay. So the same thing presented, expressed in another form. So these are the examples. Bottom profile is the X-ray diffraction pattern for a powder sample. Full width at half maxima, that you can determine using any plotting software like Origin, Excel, or any other software, and then use that values. So the same thing you can also do by rate-well structure refinement. That is quicker if you are experienced enough. Otherwise, for basic learners, you use any plotting software. Okay. This is the table. The peak position for different peaks. Okay. And then the peak broadening, and then different components. Okay. Sine theta term and cos theta term, and that's plotted. Since crystallite size determination using Scherer formula, we have used only one diffraction line. Whereas in Williamson-Hall plot method, we use multiple peaks, full width at half maxima of several peaks. Okay. So this is the real case study for a nanocrystalline sample for different composition of zinc copper ferrite, where the Williamson-Hall plot analysis has been done. So for different peaks, you can see the data point which is fitted by a line. And then using the slope of the line and intercept, you determine the crystallite size and lattice strain, how it varies with the composition. So crystal growth kinetics gets modified when you modify the composition. That's why this kind of dependency you get. Okay. One can also have some idea about crystallite shape, but that definitely requires the rate-well structure refinement. That is a very advanced characterization. So common researcher or a beginner cannot do that. You need lots of knowledge of fundamentals of crystallography. Okay. Another important thing that you often do in your experiments, in your research, that is lattice parameter. That is very important. That you need to know about and that you report in your research paper. Okay. So what are lattice parameters? So when we have regular periodic arrangement of atoms, we can define a small cell. Okay. Considering atoms at corners, we can define a 3D cell. Okay. Now, at one particular position, we choose the origin, and then 3 directions, we look for the repeat period. Okay. What is the periodicity in these 3 directions? Normally, we try to choose orthogonal axis. Non-orthogonal axes are also chosen depending upon the type of the crystal system. Okay. So one along X we identify as A lattice parameter, that's repeat period. Along Y, the repeat period is termed as B lattice parameter. Along Z axis, the repeat period is termed as C parameter. Okay. and then angle opposite to A axis in between B and C, that is alpha, angle opposite to B axis between C and A, beta, and this gamma. Okay, that is the primitive unit cell that normally one chooses during crystal structure analysis. But one may have non-primitive unit cells, and lattice parameter can be quite larger also. Okay. Now, depending upon the type of lattice parameter, different kind of unit cells one may get corresponding to different crystal systems. So in triclinic, alpha, beta, gamma, all three angles are non-90, and A, B, C, three lattice parameters are unequal. Okay. Whereas in cubic system, the three angles are 90. So most symmetric system is cubic, least symmetric system is triclinic. And A, B, C, they are all equal. Okay. So this information you can get any textbook, you are well familiar with. So people often do the mistake that you are having such a crystal parameter, this is belongs from this crystal. But that is not the precise definition. A particular type of crystal system is defined by what sort of symmetry is present. So a lattice parameter, so you know, in a cubic system also, you can define a tetragonal lattice parameter. Just you need to choose a non-primitive cell, that's all. Okay. So choice of the unit cell is yours. So that's why based on the unit cell or lattice parameter type, one should not be very precise about what type of crystal system is there. Okay. So minimal symmetry involved, say one fold or one bar rotation axis, that defines triclinic. A two-fold or two-bar rotation axis monoclinic. Likewise, different symmetry elements, they define different crystals. So often in many analysis for trigonal rhomboidal crystals, it is easier to choose a hexagonal unit cell. So as per crystalline symmetry, the crystal is trigonal rhomboidal with 3 or 3 bar rotation axis. But it is easier, एक लेक्चर में अभी फोन कर रहे हैं, it is easier to choose a hexagonal unit cell and do the crystallographic analysis. Okay. So in that case, you may get a lattice parameter similar to the hexagonals, but it is not hexagonal. It is basically rhomboidal, trigonal. Okay. So that one should not get confused. Okay. So how to determine the lattice parameter? So the exercise is called as indexing. Indexing of the diffraction pattern, that is first step, where you define that what sort of crystallographic planes are contributing to the crystal diffraction peak position. Okay. Just excuse me. Hello. आधे घंटे बाद फोन कर रहे हैं. Okay. Sorry. So indexing of the diffraction pattern is the very first step. So here you need to identify from which set of parallel planes a particular diffraction peak is coming. Okay. And how to do it? So the first easiest way is look for the international diffraction database. So if you are having the diffraction pattern in the database, you can try to match having one-to-one correspondence with the peak positions, and then you identify this is the indices. Okay. Otherwise, you need to have some analysis that we will try to discuss little bit. Just wait. Okay. So how we define the Miller indices? So Miller was a scientist who devised this method just to identify different set of parallel atomic planes. So when you have a crystal, okay, a 3D crystal, it is always possible to define different set of planes, and interplanar spacings will be different. So diffraction, when taking from a different type of plane, there will be different two theta positions. So one need to identify that this set of plane is contributing. So to identify that, Miller indices are used. Okay. So most of you must be aware of the method of determining the Miller indices. Okay. So first you define the axis, ABC axis. Then we determine the intercept for a particular plane about these axes. And then we take its reciprocal, and then we convert into integral numbers by multiplying with some common factor. That gives the indices, and they are denoted by three numbers, H, K, L, which are always integral values. Okay. So this is the example. For a cubic crystal, a plane about which is intersecting the x-axis, you have 1, 0, 0 indices. Okay. A intermediate plane in between 2, 0, 0. Another intercepting x and y axis 1, 1, 0. Okay. So that one can get details in any textbook, crystallographic textbooks or solid state physics textbook. Okay. Now suppose you don't have the database for the material. You have prepared a new material or you have got a new pattern. So you need to use analytical method. Okay. And nowadays there are standard softwares also which imply the analytical method, but they do all the computation, all the calculations for you. Otherwise, you need to use the peak positions and then de-spacing and then use the calculator and do the calculation. Okay. So ICDD database, a software, DeepWall is one software. There are many available freely. One can Google search and use it. Okay. Analytical principle. So what is the basic principle? Suppose we take a cubic crystal. You know the Bragg's law. Lambda is equal to 2d sine theta. D is the interplanar spacing for different set of parallel atomic planes. Okay. So one can devise this formula for a cubic system, lattice parameter A divided by root h square plus k square plus L square, the Miller indices. That gives the interplanar spacing, DHK. Okay. Now using this formula and Bragg's law, you can see lambda square will be given as 4a square sine square theta divided by h square plus k square plus L square. You can reorganize it. You will get this kind of expression. Now, lambda is known. A is some fixed value. Okay. Both are constant. So in that case, h square plus k square plus L square, that will be proportional to sine square theta. Okay. So this is the standard expression. So using that, one can determine the Miller indices of different peaks. How? So 2 theta values for different peaks. Then calculate theta, peak position, sine theta, sine square theta. And then you divide with different factors, say different integral numbers, 1, 2, 3, 4, 5, as permissible from this expression of h square plus k square plus L square. And then you will get some definite ratio as tabulated here. And depending upon that ratio, you will get the same common factor. And then you can identify What are the HKL values? So if ratio is 3, it means HKL that has to be 1, 1, 1. If ratio is 4, that means it has to be 2. Any of these. Okay. So these things are given in standard textbooks. For more details, you can consult. BD Kulti is one very good book for crystallographic analysis where you can get the details. Now, as you know, peak position theta is important. Using that, you are determining the theta. So if there is any error in theta determination, that will introduce error in sin theta value. And that will introduce error in everything. Okay. So when you determine the lattice parameter, the value can differ. Okay. So you can see this table. So sample is same, but corresponding to different peaks, you are getting slightly different lattice parameter. What is the reason? So peak positions are not very accurately determined. So some of the peaks, they are giving same parameter, while others are different. Okay. So incorrect peak positioning is the reason behind that. So normally people use software to determine the peak position, or you can manually measure the peak position. Just zoom the profile in any plotting software and then get some estimated position. If there is a asymmetry, that can give some error in peak position determination. As I mentioned earlier, K alpha 1 and K alpha 2, two peaks you get in diffraction pattern. So you can see K alpha 1 peak is this one, K alpha 2 peak is this, slightly adjacent to that. Okay. So in that scenario, you need to pick two peaks, deconvolute the two peaks, and then determine the peak position using some plotting software. Okay. There are advanced profile matching analysis that is inbuilt with the rate-weighted structure analysis that one can do again to determine the lattice parameter. So I will not go into those details. Okay. So this is the profile fit that has been done by profile matching analysis, not a rate-weighted analysis, profile matching analysis, but that needs the same kind of knowledge. I will not cover here. I will not discuss. But this also gives the lattice parameter, precise lattice parameter. Okay. So this I will skip because there is another speaker. So now you can see the peaks are fitted by profile matching analysis for different compositions of the samples. You get the peak position as well as lattice parameter. So that one can do. By indexing, you can determine the repeat period, lattice parameter. Okay. And if you need to know the interatomic distances or bond lengths or bond angles, so you need to definitely perform rate-weighted structure refinement where we provide the entire information of the structure fact. Okay. So there is another speaker who will tell about these things. Okay. Bond length and bond angle calculation that requires the knowledge of rate-weighted structure refinement. Okay. Now, there are different crystallographic softwares available free of cost as well as license-based where you need to purchase. Okay. So this is one website, CCP14, that you can Google search where you can get lots of crystallographic analysis software. Okay. And then there are textbooks. Pulti is a very good textbook for crystal structure analysis. Many of you might be well aware of the crystallographic analysis textbook. Another important caution one should take whenever using a software for crystal structure analysis. So it works on certain parameter. You give some peak position, strive to index it. It will give lots of solution corresponding to different crystal structure. So it's up to you to identify which solution is correct. So people often do mistake while using the standard software for indexing, for using the standard software to determine the lattice parameter. So one should always cross-check or get the advice of the experts who are well known to crystallography that whatever values you are getting, is it correct or not? Often people report incorrect lattice parameters. Okay. Sometimes it's smaller than the bond length. That's quite erroneous. Okay. So this is definitely thanks to my research scholars. So we learn a lot from them and they contribute to our publications and research career. So thanks for kind attention. There will be definitely many queries and questions that I will be happy to answer.
Um, I think so, sir. We'll wait a minute for questions. If anybody has question, please write on the chat box. If any participant has any query, you can either raise your hand or write it in the chat box. I think there's one question, sir. Name the software for determining the peak position.
Well, normally the X-ray diffraction machines which we use, they have inbuilt software. So when you record the diffraction pattern, you tell the operator that give me the peak position, they provide you that information. But sometimes they are incorrect. So in that scenario, you need to do it manually. Okay. So only then it is better to use a plotting software like Origin or any other plotting software. And then you zoom individual peaks and look manually for the exact peak position, or you deconvolute the peaks. That can be done in Origin also or Excel also, and that also gives you the peak position, 2 theta position.
Thank you, sir. The next question is, please highlight the importance of FWHM and strain when we go for residual stress measurement.
Okay. So if you need to measure the strain broadening, definitely you need to go for Williamson-Hall plot analysis. So strain can come from big variety of reasons. One reason is that when you prepare the sample, so for converting into powder, you may need to crush it, make it fine powder. So that crushing can also introduce strain. So normally people, what they do, they anneal it at some finite temperature, say 500 degrees centigrade, 600 degrees centigrade for certain hours, just to remove that inbuilt strain. But that cannot be always done in thin film analysis. Or sometimes you have nanocrystals, annealing will grow the size so that you don't need. So in that case, there can be strain contribution. Another contribution comes, suppose you prepare a solid solution, where at the same atomic size, many atoms are there. So what will be the scenario? Size of each element is different. Ionic size or atomic size will be different. See, if a bigger atom is sitting at the smaller atomic site, it will introduce strain in neighboring regions. So that also comes as the strain contribution. Okay. So all these factors contribute, and then Williamson-Hall plot analysis gives you the strain contribution. The same kind of analysis you can also do in Rietveld structure refinement, but I will not go in that.
Thank you, sir. We have another question. Can we use crystallographic open database instead of JCPDS card or ICDD database?
Yeah, definitely. Definitely that can be used. Even you may use research papers. So people normally publish their data. They give the crystallographic information. They also give the lattice parameter and scale indices. There are some softwares where you just give the lattice parameter and space group, and then it can generate the peak positions, peak values. In fact, ritual structure software also does this exercise. So you simply provide the structure factor information and lattice parameter, other information, it can generate a data where you can get all the information. The only caution is if some material is new, some beginner has done some analysis, their analysis may be incorrect. So you have to check it. Whatever paper is reporting, is it correct or not? That's all.
Thank you, sir. We have next question from Shelja Saxena. How much error is acceptable in peak position if we compare with JCPDS?
Normally it will exactly match. But during data collection, sometimes slight shift is there. So 0.02, 0.04, these kind of shifts may be there. Okay. So second decimal place, that can be permissible. Sometimes the lattice parameter of your sample may differ from whatever is reported. Reason is different. So you prepare nanosample. Different crystallite size, the unit cell may have different unit cell volume. That is well known, reported in many systems. So peak positions will slightly shift. Then what you have to do, you just look for one-to-one correspondence. Say peak, say around 20 degree. There is another peak close around 20.05 or say 20.1. So that much shift you can accept, but all other peaks will also be shifted accordingly. The only thing is you have to go for one-to-one correspondence. There should not be any extra and additional peak. Only then you can accept that kind of.
Thank you, sir. We have two questions related to. There are two questions related to Ritfield refinement. One is which software is required for Ritfield refinement, and second is how and where can we get the CIF file of composite materials for doing Ritfield, Ritfield refinement.
So basically there are many softwares available free of cost. One can Google search and download. Most user friendly is foolproof. So most because it is easy to handle. Say beginner can easily use foolproof. You just type in Google FULLPROF. So you will get the link. You just download it. There are many versions depending upon your window environment and software which is using. There are many others, GSAS, BGMN, Retica, DBWS. But most user friendly is foolproof. One can use any sub. Okay. What was next question? There was another query.
What about sir? Next about Ritfield refinement. How and where can we get CIF feel of composite material?
Yeah, CIF. So basically, this database, ICDD database, they also maintain the CIF file. Okay. So you can request them to get it, or you can simply write directly to the researcher who has published this. You simply write them that please share your CIF file. So normally they honor it. So they send you. Otherwise, there is another easy way out. If you are having another similar material, say sodium chloride and potassium chloride, both are having similar structures. So if you are not having the CIF files for sodium chloride, you can use the CIF file of potassium chloride. There will be only the difference, slight difference in lattice parameter, slight difference in peak position. So when you perform the ritual structure refinement, the software will take care of it and it will give you the correct value. So any known material where the atomic positions are given, space group and lattice parameter is given, which is similar to your compound, those values you can start for ritual structure refinement. Later on, you will get the correct value of yourself.
Thank you, sir. We have one more question. What about the XRD data for multi-material compounds like HEA? What is a better way to get the crystalline structure for these materials?
Multi-material?
What about XRD data for multi-material compounds like HEA? And what is a better way to get the crystalline structure for these materials?
HTA? What is HTA?
HEA, sir.
It's some short form, I think. Anyway, so if you are having, say, multiple phases, so I already introduced earlier that you have to do phase identification. So you have to index the sample for multiple peaks, and then you have to identify which particular peak correspond to which particular compound as per the JCPDS data. Now there can be some problem. Suppose one particular compound, its some other peak is overlapping with the other peak of another compound. So two peaks are overlapping. So then a confusion may create. So it is advised to ignore such peaks. You look for only those peaks which are not overlapping and then identify. There is another important. Suppose you are having a two-phasic material, some impurity peak is there. Okay. Say multi-phasic material, impurity phases are there. So when you start doing the analysis with standard database, first look for the strongest peak of a particular compound. Okay. If that strongest peak is present, only then go for the next strongest peak. If first strongest peak is not present, there is no question of the presence of other peaks. You need not to match for all the peaks. First you check for first strongest peak. If first strongest peak is overlapping with some other peak, there are 2-3 peaks together, then you go for next strong. Okay, so that is the strategy of doing the analysis.
So
Yes.
it was actually the participant was asking about high entropy alloys. So this question was pertinent to high entropy alloys.
Yeah. So high entropy alloys, it's the same scenario.
Yeah.
So
Thank you, sir. We have another question. How can we neglect the very small impurity peak?
That depends if your material can afford it not or not. So basically it depends upon the type of the material and which sort of physical properties you are looking in. Suppose you are measuring the dielectric constant. Okay. In some oxides, if there is very small impurity, they may not affect its dielectric constant. Okay. But if you are looking for, say, electrical conductivity, so small impurities can contribute. So which sort of property you are looking, which type of material you are dealing, that will decide what fraction of impurities one can
thank
use.
you. There is another question.
Yes.
What
Connectivity was broken. Just repeat it.
Yes. Name of the software for indexing diffraction patterns.
So Foolproof also does. And then Dickwool is, I have mentioned one website, CCP14. So you can go to that website. There are many softwares that you can download. Or simply Google search indexing X-ray diffraction pattern indexing software. You will get many. There are many available in market.
So we have another question. Is there any relationship between the plane and peak intensity?
Plane and peak intensity. So basically peak intensity that you define by structure factor unit. Okay. So structure factor formula, if you remember, so it involves the atomic coordinates, X, Y, Z, type of the atom that comes under atomic scattering factor. So how many electrons are there in the atom? And then SKL values also. So you have the exponential term, exponential twice pi I hx plus ky plus lz. So SKL values, they also affect the intensity which you are measuring. So definitely they have the role. So for one SKL, it will be weak. For another SKL, it will be strong. That you can theoretically calculate. Yes.
Thank you, sir. I think that's all from the question answer section. Thank you, sir, for elaborating on fluorescence spectroscopy, X-ray diffraction, mathematical analysis applications, and sharing the knowledge on important websites and books, which shall be useful to our participants, I hope. And most importantly, satisfying the most queries, almost all the queries of our participants. Thank you so much, sir, for sparing your valuable time with us. And
So
I hope in future we shall have
I thank the
collaboration.
organizers for giving this opportunity to interact with the young researchers, young minds, and thank all the audience for their patience to be here with me. Thank you.
Thank you, everyone. Thank you so much, sir. We shall be in touch with you, sir, for future collaborations. Thank you, everyone. With this, we come to the end of this session, morning session. The next section will begin at 2:15. Please join after the lunch. Thank you so much. Sir, with your due permission, may I begin, sir?
Yeah. Can you see my slides?
Yes, sir.
Yes, sir. Okay.
So can I begin, sir?
Yeah, definitely.
Good afternoon, everyone. I once again welcome you to the post-lunch session of National Workshop on Advanced Synthesis and Characterization Techniques organized by Amity School of Engineering and Technology, Amity University, Madhya Pradesh. It is a proud honor to have with us Dr. Irdesh Mishra, Professor in Physics at MMB Section, Department of Physics, IIT BHU, Varanasi. Dr. Mishra has done his BSc, MSc from Kumaon University, Nainital, and he has done his PhD in the field of excited state dynamics of proton transfer and applications from, again, Kumaon University, Nainital, with under the supervision of Professor H.B. Tripathi and collaborators Dr. D.D. Pant, KU University, Nainital, and Professor N. Satyamurthy, IIT Kanpur. Dr. Mishra has been research associate of CSIR at Photophysics Lab, Kumaon University, Nainital from 2003 to 2006, and then a DST Young Scientist at Biophysics Unit, IIC Bangalore from 2006 to 2008. He has done his postdoctoral work with Professor Lakovich at Center of Fluorescence Spectroscopy, Maryland, USA, and Professor Grattan at Laboratory of Fluorescence Dynamics in 2006 with Professor Geddes at Institute of Fluorescence, UMBI, Maryland, US. Dr. Mishra has worked as an assistant professor from March 2008 to September 2017, and then associate professor from September 2017 to September 2020, and now he is professor from September 2020 at IIT BHU. He has a vast teaching and research experience of more than 17 years. He has been under him, more than 12 students are doing PhD. Some have been already awarded, and 15 students have done MSc dissertation under him. He has research grants and completed projects. He has completed projects from INSA New Delhi, IOE BHU, and IOE transactions of more than 40 lakhs. And He has projects from DST, UGC, and DCT IIT BHU. He has published more than 70 papers in international and national journals and conferences. He has established experimental and computational electron spectroscopy lab with equipment such as spectrophotometer and spectrofluorometer and Gaussian FTD software. He has organized more than 4 winter schools and conferences, and he has 13 winter school and refresher courses to his credit. He has been invited to lectures for oral presentations and conference proceedings more than 20 times, or I'll say more than 40 times. He has total citations of 1800, an H index of 26, I-10 of 44, and I-10 20 and 40. His field of specialization is steady state and time domain, ultra-fast fluorescence spectroscopy, microscopy and applications, electronic structure calculations, plasmon-coupled fluorescence, thermoluminescence, and electron luminescence. His current research interests include surface plasmon-coupled metal-enhanced fluorescence study of fluorescent conducting polymers, near-field effects of charge transfer, development of multifunctional nanomaterial for luminescence, solar collector laser materials, etc. May I now request Dr. Mishra for his talk on basics of fluorescence and spectroscopy and applications. Please, sir.
Thank you, Dr. Bhatia. I want to make one correction. I am not in IIT BHU. I am in Banaras Hindu University.
Oh, sorry, extremely sorry, sir. I interpreted it.
No problem. So thank you very much. The title of my presentation is Fundamental Fluorescence Spectroscopy and Applications. Fluorescence spectroscopy actually a tool to understand the photophysics, photochemistry, and photobiology. And it is a huge application, not only in the field of the chemistry, physics, and biology. Even then, nowadays, it is utilized as a tool to characterize the materials the people are synthesizing material science. So these are the basics of the fluorescence spectroscopy, first explained by Professor Jablonski by the electron energy level diagram. Actually, absorption is this is the electronic energy state diagram in which whenever molecule absorb radiation, this is a femtosecond process. And when the electron jump, when they absorb the photons, they go in the excited state. And in the excited state, after excitation, it relax and come back to the lowest vibrational level of the first excited state. This is the S1 state. From it, it may go from the singlet to triplet.
Sir, sorry to interrupt you. Can you go to slideshow mode so wide this will?
Okay. Now you can you see?
Yes, sir. Yes,
okay.
Sir. Fine.
Okay. Okay. So when we go in the when we excite and come back to the first excited state, from the first excited, there is a probability to go. The electrons can go to the triplet state or can radiative emit to the and come back to the ground state. Okay. So if it come back to the S1 to S0 by radiatively, it is known as the fluorescence. And if come back from the triplet to singlet radiatively, then it is the phosphorescence. But sometimes radiation goes non-radiatively also. Transition when it is jumping from the excited state to ground state, sometimes radiation goes to the non-radiatively also. So this is known as non-radiative transition. This phenomenon from singlet to singlet conversion, this is known as the internal conversion by the vibrational relaxation. And when it goes from singlet to triplet, this is the inter-system process. So these are the simple terminology of the fluorescence spectroscopy. Okay. And here is the potential energy diagram. This shows the difference between photophysics and photochemistry. When we excite the sample and it goes in the same potential energy curve, potential energy well, and come back, so this is known as the photophysics. So this portion is photophysics. But if in the excited state some reactions takes place and potential started to change, this is known as the photochemistry. Okay. Similarly, in the ground state, dark reactions can take place, and ground state complexes formation is also known as the ground state reactions. Okay. So the fluorescence spectroscopy, basically there are two parts: steady state and time domain fluorescence spectroscopy. So in the steady state, generally what is the fluorescence? This is the electromagnetic radiation. When they strike, this is, let us suppose this is a water bottle containing some minerals. So when we excite this one, when we expose this sample by the UV radiation, it becomes bluish. This indicates this the fluorescence is coming out. So whenever light interact with matter, there are two phenomena takes place. Either it absorb the radiation or scatter the radiation. On the basis of scattering, there are two processes: elastic scattering and inelastic scattering. So this part of the scattering process gives the information about the vibrational nature of the molecules. It gives the information about the vibrations of the molecules. Okay, Raman spectroscopy and other. But here I am talking about when the molecule absorbs the radiation. When they absorb the radiation and goes in the excited state, there are plenty of reactions can take place in the excited state. Like here, it gives the fluorescence, phosphorescence. Just a minute. Fluorescence, phosphorescence. There may be intermolecular charge transfer takes place, conformational takes place, electron transfer can take place in the excited state, proton transfer, energy transfer, excimer formation. So all of these kind of reactions information we can collect from the fluorescence spectroscopy. If we have the basic fundamental about, if we have the knowledge about the fundamental of fluorescence spectroscopy, we can study all kind of these kind of reactions. And or not only that, we can find out the change in the dielectric property, change in the reflective index, change in the conductivity, hyperpolarizability. These kind of all information also be influenced by the fluorescence properties of the molecules. So why fluorescence spectroscopy? First, it is very sensitive. Even we can detect single molecule by this spectroscopy. It is very selective because it's different amount of different kind of functional groups gives different kind of information about the fluorescence, about the molecular system. Secondly, and it has a wide time scale, femtosecond to second. And it is very sensitive towards the environment. Like if we change the electric field, its fluorescent properties will be changed. If we change the viscosity, the fluorescence property will change. Polarity change, change the fluorescence property like that. pH, temperature, and ionic environment also change the fluorescence property of a molecule. So this kind of information, if we want to make the viscosity probe, we can make the with the study of the fluorescence spectroscopy, we can make the viscosity probe or polarity probe, pH probe, like that. Temperature sensors. These kind of sensing properties can be developed with the help of the fluorescence spectroscopy. So what is the basic difference between steady state and time domain? Here I show that in the steady state measurement, we take the source from where we excite the sample and we detect the radiation that is emitted from the molecule. Okay, so this gives excited state emission spectrum. And here in the time domain, we will study how much time molecules stay in the excited state. So this gives information about the time domain information, time domain measurements. So basically the outline of my talk is like that. Introduction, basics of UV visible absorption spectroscopy. Before going to the fluorescence measurement, we have to know about the absorption measurement. The second thing, the fundamental of frequency domain fluorescence spectroscopy. The third is fundamental time domain fluorescence spectroscopy. Then I will teach something about the instruments, the light source, how the monochrometers work, how the detector work, like that. And then instrumental architecture, spectrum analysis, limitations, applications, and if time permit me, I will tell you the recent advancement in the fluorescence spectroscopy, that is the near field fluorescence spectroscopy, and I will tell something brief about the fluorescence microscopy. But if time permit, then only I can. So what is the absorption spectroscopy? So whenever light passes through the or interact with the molecular system or atomic system, let us suppose we have a liquid sample. This is the liquid sample, and if it is transparent, then the light will pass it through this. But there are the molecules. These are the molecules, and when the electromagnetic radiation passes, that is disturb the electronic clouds of that molecule. So it creates a dipole. The change in dipole moment, it goes in the excited state whenever the absorb the radiation. goes in the excited state. So this is the absorption process. In the solid samples, we generally make the sample, we generally absorb the absorption in the reflection mode. Okay, like this. This is the absorption spectrum of the atoms, molecules, and inorganic. So in the case of the atoms, like the rare earth ions, the absorption will always be a sharp. Why? Because it's atomic. They are only electron states are there, no vibrational, no rotation. But in the case of the organic molecule, when the atoms started to combine and they form the molecules, there are a lot of vibrations started to take place and rotational motions are also started to take place. Due to that, their electron states are perturbed and their band is developed. So in the case of the organic molecule, the absorption will always be broad. It look like there is that much FWHM is there. In the general and generally in the inorganic molecules, the absorption is quite broad. It is like this. So how the complexity started when you increasing the electrons from in the number of electrons in the outermost orbits, they started to increase. Simple difference is look this is the hydrogen atom. In the case of the hydrogen atom, it has only one electron. The absorption, the fluorescence spectrum looks like this. This is the so this is the absorption spectrum looks like this. Sorry, no, this is the fluorescence spectrum looks like this. But as soon as we increasing the number of electrons in the outermost orbits or in the system, like in the neon has 10 electrons. So the emission light started to increase. The complexity started to increase. When there is 80 electrons in the atomic system, it's the emission spectrum looks like this. Okay, but in a molecular system, when the atoms combine and they form the molecules, so this is the molecular system, and when the radiation is strike on this molecule, look, the charge cloud is shifted. When they absorb the radiation, their charge cloud is shifted, and due to this shifting of the charge, this shows the absorption band nearly about 250. There are 250 electrons. Okay, so it gives nearly absorption at about 300 nanometer. So this is the atomic transition and this is the molecular transition. So in a molecular system, I am basically talking about the molecular system because molecular systems gives broad emission and broad fluorescence. So in a molecular system, there are three kind of transitions can take place. Let us suppose this is a molecule. This benzene molecule contains CH3 group and COH group. So there is a double bond O. They are two non-bonding electrons. They are single sigma bond and they are the double bond. So there is a possibility of three kind of transition. N to pi star transition. This non-bonding electron excite and goes in the excited state, or pi electrons can excite and goes in the like that pi to pi star transition and sigma to sigma star transition. And there are some N to sigma star transitions also and N to pi star transition also. The range of the sigma to sigma star is generally lie less than 150 nanometer. While in the case of the pi to pi star transition, they lie between the 200 to 800 nanometer. It lies between UV and visible region. While N to pi star transition generally lie 150 to 300 nanometer range. Now I have a question for you. You know, water molecule, this is the H2O, and H2O is transparent for the visible light. Why? Can anybody tell me about this? Why the water molecule is transparent for the visible light? Have any idea? Can you hear me?
So is it because of the order of that nanometer and the wavelength of the visible light?
Pardon?
Is it because of this size of that nanometer and wavelength of visible light is of the order of?
No. This is not the answer. You know why the water is transparent?
Sir,
The
because
region-
all of the light is reflected back from the water, all of the visible light.
No, it is not reflected. The whole light passes through the water. You know, water is transparent. So it means the whole visible light can pass through the water. The reason behind that, in water there are H2O, one hydrogen, two hydrogen and one oxygen, and they are bounded by the single sigma bond. And to excite the sigma bonds, we need very high energy. Look, this sigma to sigma star transition 150 nanometer. So to excite the water molecule, we need 150 nanometer energy wavelength. Okay. And the rest of there is no pi to pi star transition. There may be the n to sigma star transition, and this is also in the visible ultraviolet region. That's why it is not absorb the visible light. The visible light is transparent. It is transparent for the visible light. Okay. Understand? Hello.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So these are the potential energy diagram, Frank quantum energy dual diagram. I think everybody knows about it. This is the absorb. This is the ground state potential containing these wave functions, and this is the excited state. Right? Everybody knows, I think, about this. I'm skipping this portion. So this is the basics of the spectrophotometer, through which we study the absorption measurement. So let us suppose this is the instrument, and this instrument contains monochromator, lamp, and detector. Okay, so this is the dual beam spectrophotometer. This is the optical ray diagram of this inside this machine, and there is a source. Generally, in the spectrophotometer, there are two kind of source: tungsten filament, halogen lamp, and deuterium lamp. Okay, halogen deuterium lamp. So whenever the UV or visible light, it produces UV visible light, it passes through the monochromator. This is here it is the prism, but you can take the grating also, and it disperses the white light into different wavelengths. Okay, then it passes through the chopper, and chopper divided into two parts, beam splitter, and one goes to the reference and another goes to the sample. And by the ratio recording method, we detect the signal in the detector. And the cuvettes may be like this. And let us suppose this is the absorption spectrum of the chlorophyll molecule. By this absorption by this absorption measurements, we can find out molar absorption coefficient, oscillator strength, transition probability. Oscillator strength means the transition probability. This is the F. F is the oscillator strength. 4.33 to the power minus 9. This is the area of the absorption. This area. Okay, and we can calculate the natural lifetime of the molecule, and we can also find out the dipole moment of the molecule or dipole length of the molecule. This is the dipole length formula. And B.R. and Lambert was the first two scientists who gave this formula. Absorption is directly proportional to concentration and path length. Okay, you understand? And by these transitions, we can find out what kind of nature of these transitions. By selecting the molar absorption coefficient value, epsilon values, we can find out which transition is which one. Generally, N to pi star transition have very less molar absorption coefficient as compared to the pi to pi star. So this transition is in the case of the chlorophyll, it is pi to pi star. So these are the basics of the major component of the spectrophotometer: light source, monochromator, sample compartment, and detector. And this is the source: tungsten lamp and deuterium lamp. Tungsten lamp generally emit in 350 to 2200 nanometer, and deuterium light source generally emit 160 to 380 nanometer. This gives the UV light. Okay, so this is the diagram of the spectrophotometer. I already explained it. So whenever the light is emitted, this is a deuterium tungsten lamp reflected, and it by the chopper, it passes to the collimator beam and goes to the beam splitter, and then finally one beam goes to the reference sample and another goes to the sample. And by the ratio recording, you detect the signal at the absorption spectrum. In the case of this spectrophotometer, generally we are using two kind of cuvettes. One is the quartz cuvette and another one is the glass cuvette. For the UV measurement for the biological samples, we are generally using quartz cuvette, and the quartz cuvette is a very interesting, but a very good cuvette. It is transparent for 180 nanometer to 3500 nanometer, while the glass cuvette generally transparent for 380 to 200 nanometer. So sample cuvettes, the quality of the nowadays plastic cuvettes are also available. They are very cheaper, but the problem is that some of the cuvettes generally dissolve in polar solvents. Okay, so there is a restriction of that, but they are very cheap. We can use it for the water. For generally, the biological people who are working in the water, they generally use this polystyrene film or PMMA film, PMMA cuvettes like that. Look this graph. In this graph, I already showed you the transmission spectrum of the glass, optical glass, and acrylic plastics, and fused quartz and fused silica. So fused quartz or fused silica are generally very useful to working in the ultraviolet region, while the glasses are sample are good for visible only. The second thing, we have to take care the solvent. What kind of solvent we are using? So concentration, the solubility of your solute molecule if you want to study any molecule, so first you have to check the solubility of that molecule in that solvent, and the ion strength of the solvent, hydrogen bonding effect also. If you want to study the molecule and if the solvent is hydrogen bonding in nature, they will change the characteristic of the molecule. So you have to be very careful. Sometimes aggregation started to take place. You have to avoid that. So you have to be very careful. Sometimes pi stacking and solvent absorption started to take place. Like here in this spectrum, this acetone absorbed in acetone in methanol, cyanide, it started to absorb 350 nanometer, right? So you cannot take this acetone as if you want to study any molecule which is absorbing in the ultraviolet region. You cannot study it. Here in the methyl cyanide is a very good system. If you want to study your system, you can use this solvent or water. Water is also transparent to ultraviolet. So these are the common cutoffs of the common solvents like that. Okay. The third thing is this is the sample effect of the environment. Like let us suppose this is your molecule tetrazine 1245 tetrazine. This is the structure of this one. In aqueous solution, its absorption spectrum looks like very broad, but when you go in the hexane solution, it gives this kind of structure, and in vapor phase it gives this kind of sharp peaks. You know what is the difference these three? Why these three are coming? Have you any idea? Because in the absorption spectrum, in aqueous solution, it makes some hydrogen bonding in the system, and due to vibrational crowding, the absorption becomes broad. But in the non-polar solvent, hexane solution, there is no interaction between solvent and solute. So we are getting the true nature of the absorption spectrum. This is the vibration. This is the vibronic absorption spectrum. Actually, what is the vibronic means? Vibronic means the electronic transition coupled with the vibrations, because molecules are not only getting excited by absorbing the radiation, their vibrations are also changed. So their vibrations are coupled with the electronic states. Okay, so this is reflected in their absorption spectrum. And at very low temperature, when you are taking in the vapor state, taking the absorption spectrum, they are a single molecule, and they are all kind of vibrations. They are appearing in the electronic states. Okay. Similarly, by this molecule, this is a very interesting molecule. When you put this molecule in different solvents, it gives different colors. Why it is like that? Because in toluene, look, in the toluene, it absorbs generally 400 nanometer light. So it passes only 500 to 600 nanometer radiation. It looks like blue. This region, the combination of this is the, this one, yellow. So this is the different solvent. They absorb different part of the radiation. So the transmitted light, it looks like that. This is not the fluorescence. This is only the absorption. Whatever the part of the white light is absorbed by the system, the rest is reflected back, and the combination of that reflected back light gives the different colors. So these are the molecules and their absorption in different solvents, their lambda max and their molar absorption coefficient. This molar absorption coefficient depends on the transition probability of the electrons of the outermost electrons to the excited states. Okay, and this defines the quantum mode of the molecule. If molar absorption coefficient is very less, the molecule is fluorescence is very less. Another thing that is very interesting, if you have a alternative single and double bonds, the absorption started to shift. Like ethylene, lambda max of the ethylene is 165 nanometer. But if you are taking two ethylene molecules by bonding one single bond, 1,3-butadiene, it is red shifted. As soon as you increase the chain length and alternative bonds, the absorption spectrum is red shifted. So this is very beautiful observation regarding the conducting polymers. And these kind of polymers are conducting because the pi electrons are getting jumping from here to here like that. It is also useful in the vision of the eye actually. And in our generally in the biology, there are a lot of amino acids. I think there are 20 amino acids. Out of 20 amino acids, there are only 3 amino acids that are fluorescent. And these are the absorption spectrum of these 3: tryptophan, tyrosine, and phenylalanine. These are the absorption spectrum of these 3 molecules. And by absorption spectrum, if the change in the environment, you can detect the environmental condition by taking the absorption spectrum like this. If the absorption is increases, this is known the hypochromic. If it is red shifted, it is bathochromic. It is blue shifted, hypsochromic. And if it is its intensity decreases, is hypochromic. So these are some terminology that is used in the absorption spectrum. And this is the absorption spectrum of our retinal eye. And this is the rhodopsin and opsin. They are some molecules that is in the eye. The rods are generally absorbed in 498 nanometer twilight vision. And the cones generally absorb 440 nanometer, 535 nanometer, and 575 nanometer. This is useful for the color vision. Absorption spectroscopy is also very useful in HPLC. HPLC is a very high performance liquid chromatography. It is used to purify the samples. And absorption is the technique which is behind this HPLC measurements. Now the application part. Let us suppose you want to understand are the ground state reactions takes place or not. So with the absorption spectroscopy, you can change in the absorption spectrum, give the information about the ground state. Like that, 1, 2, 4, 5 tetramethyl benzene, it is started to absorb from 400, like that. Another molecule, that is the acceptor molecule, tetracyanoethylene. This is the another dot molecule absorption. This is also started from the 400. So both the molecules started to absorb only the ultraviolet part of the electromagnetic radiation. But when we take the solution of mixture of these two solvents, it started to absorb from 600, and there is a broad absorption at 500 nanometer. This indicates the ground state charge transfer band form when these two mixtures solutions are mixed. So this is a very interesting spectroscopy. Through this, we can study about the charge transfer in the ground state. Similarly, in the salicylic acid. Salicylic acid, this is the absorption spectrum of salicylic acid. It is generally absorbed in the ground state like that. This is the absorption spectrum. But as soon as we increase the concentration, a new band started to appear at 350 nanometer and its intensity started to increase. And this is the indication on increasing the concentration, the appearance of a new band, this indicates this is the dimer formation or oligomers formations. Okay. So by the help of the absorption spectrometer, we can find out whether dimers are formed, charge transfer band are formed, what is happening in the ground state. So whatever you want, whatever the information we are getting in from the spectrophotometer, they give a different kind of information about the molecular system of your interest. With the help of this absorption spectrometer, we also determine the pK values. Okay, like that. Here we are changing the pH and we are observing that this emission 605 nanometer emission intensity increases and this is decreases 455. And when we are plotted at absorption at 650 nanometer with pH, we are getting this kind of curve. The middle part of this gives the information. The pK of this solution is 4.8. So with the help of this spectrum change of this pH, so we can find out the pK value of the our molecular system. Look, this is a very interesting molecule. When it is when there is added proton, its color is yellow. When we remove one of the proton from the system, its color becomes blue. With the help of this spectroscopy, absorption spectroscopy in material science, we can also find that the size of the nanoparticles we can also find the band gap of the materials which we synthesize in our lab. Okay, so these are the very interesting. I think you people, some of you people are doing this kind of research on material science. You can find out the band gap by the tau plot. With the help of this absorption spectroscopy, you can also find the ground state reactions. Let us suppose you are doing some experiment like this molecule. When you are exciting this molecule by this wavelength, this light, a particular wavelength of light, and in every 5 minutes you are observing the change in the absorption spectrum. In every 5 minutes the absorption spectrum is started to change, and after 60 minutes you will find that the absorption looks like this. So let us suppose these are A, B, C, D, E. They are the absorption spectrum in different time scale with the exposure of the UV light of this incident light, 455 nanometer incident light. If you plot the concentration versus time, the intensity of A is decreasing. The initial compound absorption is decreasing, and the second B is increasing and then decreasing. The C is increasing and up to 300 minutes, and after that it is decreasing, and D is started to increase on. So with the help of this, we can find out the ground state reaction. What is the rate of formation of A to B, and then B to C, C to D, like that. So this is the photochemistry part. Okay, I already told you about this. With the help of this, we can also find the change in dipole moment and change in polarizability by applying the electric field in the absorption spectrum in the system. Let us suppose you have a film that contains your molecules, and you put that and you apply the electric field around it, and when you excite the sample, if there is a change in absorption, spectrum looks like this. Without electric field, its absorption looks like this, but in the presence of electric field, if its absorption is decreasing and the FWHM is increases, this is the broadening. Okay, and if it is shifting, if your absorption is after in the presence of electric field is absorption blue or red shifting, this gives the information about the change in the polarizability. So this is the second order derivative, and this is the first order derivative. And if you take the absorption spectrum's first order derivative, if you match with these two, so you can find out what amount of change in the dipole moment and what amount of change in that polarizability takes place. Like that, this is the absorption spectrum of a compound. In the PMMA, absorption looks like this. The first derivative of this is this one, and this is the second derivative. And this is the electroabsorption measurement when we apply the electric field. This is the simulation curve, and what we found, this spectrum well match with the second order. So it means that there are change in polarization takes place a lot. So with the help of the absorption spectroscopy and electroabsorption spectroscopy, we can find the change in absorption and change in polarizability by these measurements. By that, there is another kind of spectroscopy, that is a transient time dependent absorption. Transient is very interesting actually. In the case of the transient, I give you the basic idea of this. There are two sources. One source excites the sample. When you excite the sample, electrons goes in the excited state, and then you excite the sample, and then you pass the white light. The first is the pump, the another is the probe. So with the help of this, you can find out the excited state dynamics of the molecular system. Okay, so this is a transient spectroscopy. I'm not going into detail about this because I have to go fluorescence spectroscopy. What is the fluorescence? I already told about that. And the first fluorescence absorption was observed by Professor Marcel in quinine sulfate solution in 1885. What he observed? Can you look this up? Can you get this animation?
Yes.
Hello.
Yes, sir.
Yes, sir.
Okay. So this is a blue glass window, and this is the sunlight. When the sunlight passes through the window, and this is a quinine sulfate solution. What this Herschel observed, this Stokes is observed. Without the wine glass, this is the wine cup. Without the wine glass, they observed the violet light only. But when they put in between their eye and this quinine solution glass, quinine sulfate solution, they observe the green light. So what is this green light? From where this is coming out? So this means when this light is passing through this quinine sulfate solution, its solution getting excited, it started to emit green light, which is because the percentage of the incident light is greater, then we cannot, without this filter, we cannot absorb it. But when we put the filter, we are absorbing the green light. So this is the first observation by Stokes. That's why it is known as the Stokes effect. So let us suppose this is the absorption spectrum of the quinine sulfate solution, and this is the emission spectrum. The difference between absorption maxima and emission maxima is known as the Stokes effect. And what is fluorescence actually? Look, in the case of the fluorescence, when we excite the electron, it goes in the excited state. Then there is the internal relaxation, and it comes back to the lowest vibrational level of the first excited state. From there, it radiatively emit the photons, and this is the fluorescence. Okay. And these are the selection rules. I think all of you know about it, so I am just skipping this. The absorption spectrum, they are in the case of the molecule to molecule, you are getting absorption and emission. Sometimes you are getting absorption and emission spectrum looks like this. This is the first one, and this is the second case, quinine sulfate absorption and emission spectrum. In the first case, this is the anthracene molecule. Look, the absorption is structured. You are getting peaks here in the absorption spectrum. Similarly, you are getting the emission spectrum. You are also getting the peaks. Right, structured emission. This is known as the structured absorption, and this is known as the structured emission. Emission is the mirror image of the absorption. It is clear? Okay. And these, why you are getting this? Because in the ground state there are number of vibrational states like that, and in the excited state also, first excited state also like this. So this corresponding to the transition corresponding to 3 vibrational levels of the first excited state. Similarly, when they are coming back from the excited state, they are vibrational levels in the ground state also, and the emission are coming in different states. So why it is structured and why it is not structured? The second one is not structured, but the first one is structured. This is the mirror image. It is absorbed due to the this is known as the vibronic emission and vibronic absorption. By this, we are getting information about the vibrations also of the ground and excited states. Generally, from the emission spectrum, you will get information about the vibrations of the ground state, and from the absorption spectrum you will get vibrations in the excited states. In the second one, there are 2 electronic states. They are overlapped, S0 to S1 and S0 to S2. They are overlapped. It is not vibronic. There are 2 electronic states are overlapped, but in the first one there are only 1 electronic state. There are number of vibrations. That's why their structure is different. That's why it is known as the electronic absorption and electronic emission. But in the vibronic absorption and vibronic emission in the first case. In the second case, the 2 electronic states are overlapped. Okay, so they are pure electronic absorption spectrum and emission spectrum. In the emission spectrum, there is nothing. There is no vibrational changes. Okay. So by these machines, and this is the spectrophotometry machine, and this is inside the spectrophotometer. There is a source that is on the xenon source. Generally, we use the xenon source because it gives the continuous light. And there is the excitation monochromator. This is excitation monochromator. Then there is a sample compartment. Then there is the emission monochromator, and then PMT. So by the spectrophotometer, we can find out the quantum yield and natural lifetime by this formula. By absorption also, by the fluorescence measurement also, we can find out the natural lifetime, and this is the formula to collect the fluorescence lifetime, natural lifetime. So measurement of the emission spectra, how we measure the emission spectra actually. So before starting the emission spectra, we have to first measure the absorption spectra. So this is the S0 to S1 transition, this is S0 to S2, this is S0 to S3. But according to Casa rule, you know, when we excite, wherever we excite, this is the higher excited state and this is the lower excited state. Wherever we excite, the emission always comes from the, this is the emission spectrum, emission comes always, this is red state and comes from the lowest vibrational level. So look, this is it absorbed nearly at 475 nanometer, but emission comes at nearly 650 nanometer. So how you collect this? Switch on your lamp. This is your lamp. Select your wavelength of, this is your monochromator. The whole white light passes through the monochromator. Select your excitation wavelength. How you select? Take the lambda max of the absorption spectrum. This 450. So your excitation will be 450. Put your sample here. When you excite your sample, the fluorescence will go everywhere. You collect your fluorescence and pass it through the emission monochromator and disperse your grating, and you will get the emission spectrum. When you rotate your emission spectrum, emission grating, you will get the emission spectrum. Okay. And with the help of this, you can find out the quantum yield and radiative light time. These are the formulas I already told you. So how you can find out the quantum yield? Quantum yield means number of photons emitted upon number of photons absorbed. Quantum is a very important parameter in fluorescence spectroscopy. So there are two methods through which you can find out the quantum yield. First is the relative quantum yield method, and second is the absolute quantum yield method. So this is the relative quantum yield method. So in this case, you will take a reference sample, let us suppose cunin sulfate or anthracene molecule, anthracene absorption and fluorescence. So anthracene quantum yield is generally 0.99 and cunin sulfate quantum yield is 0.55. So if you will take, it depends on in which range you are working. If you are working in the visible range, then take the sodium fluorescein as a reference. But if you are working in the ultraviolet or this below 400 nanometer or 450 nanometer, then take this cunin sulfate as a standard. Okay. So this is the quantum yield of the sample. This is the formula. Quantum yield of the sample upon quantum yield of the reference. Intensity of the sample upon intensity of the reference. And these are the absorption measurement, optical densities, and the reflective index of the solvent in which you are putting your samples. So by this ratio recording, by this formula, you can find out relative quantum yield. But if you want to measure the absolute quantum yield, this is the quantum yield measurement system. This is also known as the integrating sphere. Okay, so there is a sphere like this. Inside, you put your sample and first measure your reflex, whatever the light you are exciting the sample. Pass that light. Look, your absorption looks like this. This is the scattering light. But when you put your sample, this sample is started to absorb the radiation. The intensity of this band is decreases, and here you are getting a emission spectrum. This one. Here I enlarge this one inside of this figure. Okay. So this is the emission spectrum and this is the absorption. So how much amount is absorbed and how much amount of emitted, take the area of these two bands. So this area ratio gives the quantum yield of the system. One of the things you have to measure excitation spectrum also. Excitation spectrum is very interesting. Actually, how you will take the excitation spectrum, I will tell you. First, look this. In the case of the emission spectrum, you fix this monochromator, excitation monochromator, and you rotate the emission monochromator. But in the case of the excitation spectrum measurements, you have to fix this emission monochromator and you have to move the excitation monochromator. So if you put let us suppose you fix the emission monochromator at 500 nanometer and you rotate the excitation monochromator from 200 to 450 nanometer. Here in this case, you are changing in these two diagrams. This is the excitation, this is the absorption spectrum, and this is the excitation spectrum. And you are moving the excitation monochromator from 200 to 600. Okay. When you are fixing the emission at 650 nanometer, look, the excitation spectrum is similar as the absorption spectrum. Actually, excitation spectrum should be similar as absorption spectrum. If it is not like that, it means some excited states reactions take place, like electron transfer, proton transfer, charge transfer, and other kind of excitoplex formation or excimer formation like that. So you can study the change in excitation spectrum. If you are getting any change in excitation spectrum, you can tell about the excited state reaction or you can tell about the change in the isomers. You can detect the isomers. So excitation spectroscopy also very important. Okay. So samples. Now there are samples. Samples may be solid, powder, solution, thin film, and crystals. So in the solution, you generally study measurement in the cuvette. So if you put the solvent, if you put your compound in a mixture and put in this cuvettes, you can measure the fluorescence in the 90-degree direction. Similarly, like the thin films, you can study the thin films, but for the powder measurement, you can generally measure the fluorescence in the reflectance mode, like that. And even the crystals, some of the crystals that contain the rare earth, they emit very beautiful fluorescence, and you can study this by placing it in the chamber in the reflectance mode. So for the emission measurement in solution, generally what happens when you pass the light through this sample compartment, this is the cuvette and this is your solution. When you excite the sample, the emission is coming out this, like that. If you put your detector here in the transmission side, in the top view, like here, when we excite the sample, it passes through the cuvette, then we will get the absorption spectrum. But in the perpendicular direction, if you put your detector, you will get the emission spectrum. Okay. So sometimes you are getting some distortion in your emission spectrum or shifting in your emission spectrum. Like this. This is an example of anthracene. If you at very low concentration, you are getting, this is the emission spectrum of anthracene. There are 5 emission bands. 4 emission, 1, 2, 3, 4. But on increasing the concentration, this intensity of the first emission band, 380 nanometer emission bands is started to decrease and redsepted. Why it is so? First, and you know what is the inner filter effect? When you measure the emission spectrum, you will appear the emission spectrum is redsepted. There is shifting in the emission spectrum. Sometimes you think that some excited state reactions takes place or some dimer formation, excimer formation take place. No, it is not like that. You have to check whether this is excimer formation or some kind of artifact. This is the artifact. This is the inner filter effect. Look, when the concentration is very low in the first one, in the first cuvette, the light passes throughout the sample. It flows the same. When increase the concentration, light passes, but its intensity is decreasing. Now in the last one, from the right hand side, the first one is here the light is not entering in the sample. It means the concentration of the sample is very high. And due to this is the concentration effect. Whatever the energy is emitting, it is absorbed by the system itself. This is the energy migration also. And due to energy migration, this band intensity is disappear. This is the artifact. When you this kind of sample, if you want to study, you have to study in the reflection mode, not in the transmission mode. In the transmission mode, you will get very weak signal and it is redsepted. Okay, and this is known as the inner filter effect. Similarly, sometimes in the emission spectrum, you are getting emission looks like this. This is a broad band, and then there is a sharp peak. When you excite in the 300 nanometer, 380 nanometer, let us suppose, you are getting a broad band about 650 nanometer, and then a peak, sharp peak nearly at 760 nanometer. So you have to confirm whether this is a signal of the signal of the molecule, that signal is coming from the molecule, or this is some artifact. If you want to check it, let us suppose you excite 300 nanometer, put a filter there. If you put a filter of 380 nanometer, and if this band is disappear, it means this is the second order of the grating, which distort your emission spectrum. Okay. Sometimes you are getting this kind of signal, raw fluorescence along with a small peak like that. So how will you check? This is the signal coming from the molecule, or it is something else. Here it is Raman signal. Raman is a scattering process. Raman is not a fluorescence. It is not coming from the real electronic states. Okay. So how you will check it? Just change the wavelength of excitation. Here you are exciting from 350. If you excite it from the 360 or 300 nanometer, this peak will be shift. If this peak is shift, then it is the Raman. Because fluorescence never shift. Only Raman signal will shift. That is the Raman stroke shift. So in combined form, if you and sometimes let us suppose your sample is contaminated. So let us suppose you are getting this kind of signal along with your fluorescence emission. So if your pure solvent gives like this emission, so you have to subtract from the signal. Then only you will get the fluorescence. Scattering Raman signal, you can check whether this is Raman or not by just shifting the excitation wavelength, or you can check the sterilite by putting the filters. Now the application part of the fluorescence spectroscopy. With the help of the fluorescence spectroscopy, we can study the exciplex formation like this. This is the first example of exciplex formation. Let us suppose there are two molecules. This is a human serum albumin or ANS molecule. This is a this is the emission spectrum of this is very, very weak. ANS emission is very weak and HSA emission is also weak. But when you take the mixture of these two, the fluorescence intensity of this is increases. Look, a new emission is getting out. Excitation of this 450 nanometer band and 300 nanometer band is same. It means this reaction takes place in the excited state only, not in the ground state. In the ground state, they are separate species, but in the excited state, they are combined. HSA and ANS molecule combined in the excited state, not in the ground state. Another example is anthracene with this molecule. And these are the emission spectrums. So monomer generally emit the monomer of the anthracene, generally the emission of the monomer is like this. But as soon as you increase the concentration of this molecule, when you are adding this molecule in the excited state, they combine with this molecule and the emission spectrum looks like this. And the excitation of this anthracene molecule and this complex is the same as the absorption of the anthracene. Okay, it means you are getting the signal from these two molecules combined in the excited state, not in the ground state. This is the exciplex formation. Sometimes you are getting this kind of beautiful shifting of the molecules emission in different solvents. Like this is a fluorescent molecule which gives different emissions in different solvents. This is the solventochromism. And with the help of this, you can by putting these values in different solvents, you can find out the dipole moment in ground and excited state. Dipole moment of this molecule in ground and excited states by this shifting, by putting these different equations, right? The another example is pyrene. Pyrene is also very interesting molecule. This is the pyrene molecule and this is the monomer emission. But as soon as you increase the concentration of the pyrene molecule, a new emission band appears at 450. Monomer emit at 400 nanometer, nearly at 390 nanometer. But on increasing the concentration of the pyrene, the intensity of the 450 nanometer band is increases, and this is the excimer formation. In the excited state, the two molecules of this pyrene molecule started to combine within 400 nanosecond. Excitation spectrum of this excimer and monomer is same. If it is not same, then it is not the excimer. If the ground state, if there is some changes takes place in the ground state, then it is known as the dimer formation in the ground state. But if it is taking the excited state only, then it is known as the excimer formation. And what is the application of this? Application of this study is we can study the biological molecules. Like here, there is some lipid layers. If you want to study that lipids are in nearby or they are very far. If they are very far, then you are getting only monomer emission. But when the lipids are very close, you are getting the dimer emission of the pyrene molecule. It means the lipids are very near. So this kind of studies will be useful to study the biological systems also. Not only biological, excimer lasers are formed only on this concept. KBR laser, excimer laser. It is based on this concept. Sometimes in the molecule system, look, this is the molecule DMABN. This is the molecule. In some solvent, like in hexane, it is not rotating. This band is not rotating, but in THF it is rotated. So that's why in hexane it gives only single emission. But when you put this molecule in the THF solvent, this benzene group started to rotate, and this is the twisted injectable charge transfer state is appear. So in the excited state, it gives the double potential well. While in the case of the hexane, it gives only the single well in the excited state. Similarly, proton transfer studies, excited state proton transfer. We can study the proton transfer studies through this fluorescence spectroscopy measurement. Look, in the first case, there is no hydrogen bonding in this molecular system. This is the CH3 molecule, and this is the oxygen molecule in the functional group. So when this molecule absorbs radiation, this is the absorption spectrum of the this molecule, ortho-methyl benzoic acid. This is the absorption spectrum, and this is the emission spectrum. The Stokes shift is very less, but when we replace the CH3 group by the H hydrogen atom, then it becomes the salicylic acid, ortho-hydroxybenzoic acid. In this case, the absorption is similar as this one, earlier one, but the emission is large stroke shifted. Why it is that much large stroke shift? Because in the excited state, as soon as this molecule absorbs radiation, in the excited state, it transfer proton from this OH to here, this one. This is the donor oxygen, and this is the acceptor. The hydrogen bond is shifted from here to here. So the proton is transferred in the excited state. And this is the femtosecond process. In 1989, the Nobel Prize goes to Professor Joel in this work. So in the excited state, in the ground state, this is the potential energy curve in the ground state and in the excited state. Excited state, as soon as absorbed radiation, this molecule within the femtosecond proton transfer takes place, and it goes here, and then it started to emit. The another application of this fluorescence spectroscopy in the biology, like most of the biological amino acids or proteins, they are not emitting, only 3 are emitting, because 3 have the strong absorption in the UV visible region. They are tryptophan, tyrosine, and phenylalanine. Okay. Now the time domain measurement. Whenever we excite the sample, it goes in the excited state, then come back. So when we plot the decay looks like this. The decay curve spectrum looks like this. And 1/3 of 1 upon 8 part is 7, where the 37% intensity decreases. This is the time of its decay. Here it is nearly about 500 picoseconds. So why do we care about the lifetime? Lifetime is very important to understand the rate of electron transfer, rate of energy transfer, distance dependence, how the rate is changes with the distance, how we distribute static and dynamic quenching, how we measure the fluorescence resonance energy transfer, how we track the solution dynamics, how we track the rotational dynamics, measurement of local fraction, microviscosity, how we detect, how we check the chemical reactions, right? In the, you already know about this, the GFP Nobel Prize in the green fluorescent protein, Nobel Prize goes to some, I forget the name of that professor. So these are the beauty of the time domain measurement. Actually, lifetime measurement or decay time measurement is more sensitive as compared to the fluorescence. It gives more information as compared to the fluorescence spectroscopy, simple fluorescence spectroscopy, frequency domain as compared to frequency domain. Okay. So there are 2 kinds of time domain measurements methods. First is the pulse one, and the second is the modulation one. So in the pulse one, this is the time correlation single photon counting. You are getting this kind of spectrum or this kind of decay curve, but in the modulation one, you are getting this kind of graphs. Here I am talking about the time domain measurement by the TCSPC, time correlation single photon counting method. So by this reactions rates, you can find out the rate of the reaction of the first excited states. And we can also detect the quantum by measuring the lifetime. by radity or non-radity. For the natural lifetime, we can find out the absorption and emission spectrum. And here we are getting the measured lifetime. With the ratio of these two, we can find out the quantum yield. So quantum is generally radiative upon radiative plus non-radiative rates. If the excited reactions takes place, then radiative upon all the excited state non-radiative reactions rates is the ratio of these two. So time domain measurements, there are different methods: real-time measurements, multi-channel photon counter measurements, strobe method, time per single photon counting method, stack camera measurement. Stack camera is very good machine, but it is very costly, and fluorescence conversion measurement. So here I am talking about the time per single photon counting. I am using this technique in my lab here in Banaras University. The concept of this, in this one, we take pulse light source in place of the continuous one. In the case of the fluorescence measurement, we use the continuous light source. But the time domain measurement, we are using pulse light source. So we pass the pulse light source, pulses of the source, pulses of the light to excite the sample, and whatever the emission is coming out, we detect to the PMT and pass the time to amplitude converter, and we are getting this kind of decay curve. And by analyzing this one, we can find out the quantum yield and radiative lifetime. And these are the fatigue parameters. This is the residual distribution. Okay. And this is time to amplitude converter is the heart of this machine. What is the application of this? Look, nowadays people are using this machine to measure the percent of oxygen or skin. If you want to analyze the skin, you can use this technique. And this, let us suppose this is the sample, a blood sample, and the blood sample pH changes with the emission spectrum changes with this pH, and this is the decay. So here you are getting only intensity is down, intensity getting down with pH, but here with pH lifetime changing, and there are two kind of lifetimes. So there are two kind of species in the blood. So it gives the more final image about the system, your molecule system. Here skin, this is the skin fluorescence, and this is the pulse reference source lifetime, and this is the skin of the this is the decay of the fluorescence skin. Okay, so this is the fluorescent decay of the skin, and this is the pulse. So we can get information about the skin solvent. This is a huge application in biology. Look, nowadays this spectroscopy also used in the heart. Time domain fluorescence spectroscopy also used in the heart surgery. Okay, and the imaging of the images, different images. If you stain the biological samples are not emitting. But when you take the fluorescent molecule with the biological samples, the different part of the biological samples give the different kind of fluorescence. And you can get, by the time domain measurements, you can understand the dynamics of these probes at that particular level. So how the time domain machine is work? So in that one, I take the pulse light source, then we take the excitation monochromator, and then we divided this whatever the light is coming to excitation monochromator two parts. The start PMT, first it goes the start PMT, and the another is goes the sample, and the from samples it goes to the emission monochromator, and then it goes the stop PMT. Then it means there are two signals, start and stop. Okay, then by the ratio by the TCSPC method, time to amplitude converter, we get the decay curve. This is the block diagram of the TCSPC machine. I am skipping this portion. So I already told you about this. We are getting in the time domain measurements, we are getting this kind of decay curve. This is the log plot, and when we analyze, this is when we analyze and fit it in the fitted this curve, we are getting by the distribution residuals, we find that this is the best fit. And here this shows the single lifetime. This is the anthracene molecule. So and it's at 4.1 nanosecond. So this is the analysis part. I am just skipping because time is not permit me about the same. So these are my labs earlier where I work in Nainital. So these are my spectroscopy lab. This is the laser. This is a time domain machine. Earlier it was that much big. But now this time domain machine, that was big machine, is now in this one, in this card. This is small one. Okay, and this is the time domain fluorescence microscope. And this is here in my BHU department. This is my time domain machine, fluorescence lifetime and lifetime machine, fluorescence and this time domain measurement. Both the measurements we can do simultaneously in this system, in this machine. So I am thus, may I know what is the, how much time I have now? Hello?
Yes, sir, we have 15 minutes.
15 minutes. So
Yes.
I am also skipping this part. I will show you some interesting part of this work. Fluorescence quenching is another important thing through which is nowadays people are using this technique to making some sensors, optical sensors. And the fluorescence quenching, again, there are two kind of fluorescence quenching, the static quenching and dynamic quenching. In the static quenching, only fluorescence intensity is changed, not the lifetime is not changed. But if the lifetime also change and fluorescence along with the fluorescence intensity, it means the dynamic quenching. I give that much brief only. And then there is another thing, there is excitation energy transfer. One molecule absorbs radiation and it transfers to the energy to another molecule and another molecule emit. This is not the energy transfer and is huge application in making the lasers, and nowadays very advanced photonic devices are based on this one. So I am skipping this part also. So look, this is very interesting one. This is a salicylic acid. In this film, the middle one contains the terbium ion, and the first one is the blue one is the salicylic acid. This is in PVA. In the PVA, the salicylic acid very strong blue emission in the under ultraviolet radiation, and the terbium film, there is no emission from the terbium. But when we take the mixture of these two, terbium with salicylic acid, it gives a beautiful green color emission. Then why it is happening? Because salicylic acid molecule absorb radiation is transfer its energy to the terbium ion, and these are the measurements. This is the absorption measurements. This is the absorption of the terbium. Terbium absorption is very weak, while the salicylic acid absorption is very strong. And when we take the mixture of these two, the intensity of salicylic acid decreases. This 400 emission is salicylic acid. The intensity of salicylic decreases, and intensity of terbium is increases. These are the terbium lines. Because terbium is an atom, that's why its emission is very sharp. And these are the decade time domain measurements. In the time domain measurements also, salicylic acid emission is single lifetime, but in the presence of the terbium, its lifetime is decreases. The decrease in lifetime indicates in the nanosecond scale. This indicates that energy transfer takes place from singlet to singlet. Okay, but here in the time domain measurement of the terbium, we are getting the rise time of about in microsecond. This indicates the energy transfer also takes place from the triplet also. So that's why when the salicylic acid molecule absorbs radiation, there's a fast proton transfer takes place, and it goes in the S1 state, this one new space in the excited state, proton transfer spaces, and it transfers the energy to the terbium atom by singlet and triplet both. So this paper published in 2008. And another application of fluorescence in fluorescence microscope, development of fluorescence microscope. The basic fundamental is here. When you excite the sample, there you put a dichroic mirror. You excite your sample, so this beam passes through this, reflected by this beam splitter dichroic mirror, and you excite the sample. So whatever the fluorescence coming out, that goes to the this camera by this mirror, dichroic mirror. So by this, the people apply the fluorescence spectroscopy to develop the fluorescence microscope. And fluorescence microscope, nowadays, a couple of years, 2 years, I think, back, the Nobel Prize goes to the development of the time domain fluorescence microscopes, confocal microscopes, like that. These are the confocal microscopic images based on the fluorescence spectroscopy. So I am skipping. Nowadays, this near field spectroscopy also developed and taking place. And what is the near field spectroscopy? Actually, in the recent advancement, near field spectroscopy, metal enhanced fluorescence technology and surface plasmon coupled fluorescence spectroscopy become a powerful tool to investigate the structure and dynamics of molecules near the surface of the metallic nanoparticles. Due to surface plasmon interaction, photophysical properties of the molecules are found to be drastically changed in the close proximity of plasmons supporting surfaces. So how it works? Look, fluorophore. When you excite the molecule fluorophore or some organic fluorescent molecule, it gives emission in every direction. But And what are the plasmons? Plasmons are collective oscillation of the electrons in the metallic nanoparticles. When we combine this fluorophore molecule with the plasmon materials, the fluorescence can be directional. This is the beauty of this one, near field spectroscopy. So it bypass the limits of classical fluorescence and optics. It improves the sensitivity and gives the direction to the flow of light. Here the Mean scattering started to take place, and this Mean scattered radiation contained the fluorescence in the particular direction. So this is the basic difference. In this one, the fluorescence intensity and lifetime change in the simple one. In the simple fluorescence, Jablonski diagram based, this is the simple fluorescence. In the lifetime intensity change similar way, but in the place of the near field spectroscopy of plasmon coupled fluorescence, they are changed in the opposite way. In the case of the simple one, no wavelength dispersion, but here the angle dependent wavelength dispersion appears in the plasmonic fluorescence spectroscopy. Okay, and the simple one is polarization depends on the molecular motion. Here, polarization depends on the electronic mode of the substrate. What kind of nanoparticle and what kind of substrate you are taking, where you have put your fluorophore molecule. And I got this kind of rings in this case, that this is separate plasmons coupled emission, and this kind of effect we will observe in the separate plasmon coupled emission. So these are some nanoparticles, silver, gold, and this one, and how the intensity changes, lifetime changes, and photostability. Very interesting. The photostability enhances a lot. I will show you some of my results. This is the silver nanoparticles with different concentration or with different thickness. So look, when we take the absorption of these silver nanoparticles, this is the plasmonic absorption band of the silver nanoparticles. Okay, and these are size of the nanoparticles. This is the first experimental evidence of the tinopal. You know, tinopal is a very interesting molecule which gives a very bright emission. When we take the absorption spectrum of this molecule, it looks like ning. But in the presence of the silver nanoparticles, its absorption enhances a lot, about 3 times enhances. And its fluorescence intensity enhances nearly 4.5 times near the nanoparticles. And lifetime it decreases and photostability is increases. So this is the beauty. This is the beauty that it provides the stability to the system. Generally, organic molecules, they are degraded in the presence of UV light, but in the presence of nanoparticles, their degradation will be decreased. They become highly photostable. Similarly, this is the observation of the DNA biomarker in the presence of nanoparticles. Generally, biological people do the experiment like that. They are doing this biomarker gel analysis, electrophoresis. But in the presence of the figure 1, you saw in the presence of the silver nanoparticles, the band is quite separate, quite clearly, rather than the figure number 2, where there is no silver nanoparticles. The second one, the intensity of the band is very high. Look, fluorescence enhances about 8 times. You know, the biomarker ethidium bromide is a carcinogenic. So it means if you apply this technique, so we can reduce the amount of the biomarker. This is another paper in which we are studying that this change in dipole moment change in polarizability effect. And this is the interesting observation. This is a conducting polymer, which I placed on a glass surface, which is ITO coated glass surface over this PQT thin film. And when we apply, this is the absorption spectrum. In the presence of the silver nanoparticle, absorption enhances a lot and fluorescence enhances a lot. But as soon as I apply the electric field, the fluorescence intensity is decreased. It means we can control the fluorescence with the applied external field. So these are the another application of this plasmonic one. I am skipping, and the another one is the fluorescence in the presence of nanoparticle depends on the thickness of the films. How much thickness is your film? If it is thin or thick. If it is thin, then you are getting this kind of emission, directional emission. But if you are thick, then you are getting these kinds of rings. We are getting a lot of rings. In the thin one, you are getting only single ring, but in thick films, you are getting number of rings. Similarly, we can identify, let us suppose this is the europium. In the presence of the silver nanoparticles, we are getting the emission in different directions. So these peaks are shows the directional emission. And these peaks, you know, in the rare earth, these peaks are some of the electronic type of transitions, and some are the magnetic dipole transitions. So in one direction, we are getting the electric dipole transition. In another direction, we are getting the magnetic dipole transition. So with the help of this, we can distinguish which one is the magnetic dipole transition and which one is the electric dipole transition. Similarly, by placing two metal layers, this is another effect. I am not going to explain this. This is one of my very interesting observation, very long back in Nainital. In the presence of the similar nanoparticles, this is the fluorescence without nanoparticles of salicylic acid and naphthoic acid, but in the presence of the nanoparticles, their fluorescence become directional. And this is the brain and eye of a Drosophila. I did this experiment here in Banaras University in biophysics geology department, Professor Lakhatia lab. And this is very interesting observation. Very low intensity of the UV radiation. That this is the brain, this is the eye, and this is the brain image of the Drosophila. But with the on the surface of the nanoparticles, the same image is converted like that. Its image is very good, right? It's highly resolved. So with the help of the nanoparticles, we can enhance the resolution of the images. So finally, in conclusion, our findings suggest a significant opportunity for the development of shorter-lived, bright, highly photon fluxed luminescent material for the multifarious application in the life sciences and photonic devices, and present an opportunity to modulating the photon flux of polymeric materials and even in the potential development of energy efficient plastics. So these are the future of the plasma coupled devices. It is a bright future. So these are some reference books if you want. And these are some Nainital in during the winters, and this is the BHU where I am presently working. Thank you. I don't know whether how much you understand because I am delivering this lecture very far. Okay, thank you, madam.
Thank you, sir. Now the house is open for any queries, questions. Participants, you can write your question on the chat box. If anybody has any query.
No questions. I don't know because I am sitting very far and I very fast I move actually. I moved very fast.
Sir, we'll wait a minute and otherwise we'll continue. We'll see.
No problem. Because, I can understand.
Yes.
How much because the audience is different. Na? You already says me that they are UG students and PG students also. Might be PG and PhD students understand this. Especially PhD students because they are using this technique in their work, research work.
Yes. Participants, you can write your questions on the chat box like we are done in the morning session.
No question, madam.
Okay, fine. If you have any query, you can please send us and we'll send to sir on his mail ID. Okay. Thank you so much, Dr. Mishra, sir, for such an enlightening talk.
Thank you, madam.
You rightly covered from basics of fluorescence spectroscopy to TCSV thread and applications, as well as fluorescence microscope, confocal microscopy, and you gave number of examples. You aptly covered the theme of the workshop. Thank you very much, sir, for sparing your valuable time with us and sharing your knowledge with us. I hope participants might have gained from the knowledge you have shared and they may be using this in their future endeavors. Thank you so much, sir.
Thank you, madam. Nice to meet you.
Thank you, everyone. So with this, we conclude the session and we'll meet again tomorrow morning for the next session at 10:15. Have a good day, everyone.